We have Harrison from Carnegie Mellon, who's going to tell us about abstraction functions as types.
All right, thanks, Ben. Thanks, everyone, for coming. I'm excited to tell you about some work that I've been doing with my collaborators, Runming and Bob, about abstraction functions as types, which is really a method for verification of data structures in dependent type theory that supports modularity. All right, so let me motivate this idea. I'm going to try to not say anything too abstract today, and I'm going to do that by using a specific example of queues. So just as a reminder, a queue is maybe a type that's equipped with an enqueue, a dequeue, and an enqueue and a dequeue operation, along with a way to start as an empty queue. And there's a pretty simple way to implement this, which is using a list. So a standard basic implementation of a queue just consists of the representation type being a list, and you start with an empty list for the empty queue, and you append to the end, and I don't know. It's a pretty basic implementation of queues, but it's obviously not so efficient. Another implementation that you might be familiar with is sometimes called a batched queue, the idea being that you implement a queue using a pair of lists, and you don't have to worry too much about the details of the implementation. Maybe one high-level thing to know is you enqueue to the first list and you dequeue from the second, unless the second is empty, in which case you reverse the first list and move it to the second. So, all right, if we had these two implementations, we can think about how they relate to each other, and we can, first, I want to pull up this quote from Liskov and Zillies back in the 70s, where they were thinking about modularity. And they said that when a programmer makes use of an abstract data object, you should only be concerned with the behavior that object exhibits. So surely then, I should be able to verify code about both list queue and batch queue without worrying which one I chose. So okay, here are a couple client programs, C1 and C2. They both take in an implementation of the queue library, and they compute a number as well as a queue using that library. And the first way that you would do this is by starting with an empty queue, enqueuing the number 1, enqueuing the number 2, and then dequeuing. Another way that you could compute the same results, ideally, would be the second client, C2, where you just say, well, I know the number is always going to be 1, and the remaining queue is going to be a queue just containing the number 2. So we'll start with an empty queue and enqueue 2. So the intended theorem, if we're satisfying the modularity principle that Liskov and Zillies were thinking about, should be that no matter which queue implementation you pick, no matter what library you choose, or what implementation of the interface you choose, then C1 and C2 should agree. In other words, if you're in the middle of a big verification about some algorithm involving queues, you ought to be able to swap out the more complicated C1 for the simpler C2. And indeed, it is true that if you plug in the list queue implementation, both of these things return the number 1 and give you the singleton list 2 representing the queue containing the number 2. But unfortunately, this isn't literally true when you use batched queues. So you'll notice if I use the first client, I'll end up with the number 2 in the second list versus the second C2 client will end up with the number 2 in the first list. So even though these are pretty similar, they're both queues storing the number 2, if I'm in dependent type theory and trying to do verification, those are different values, and I can't just plug one for the other. So this is, by the way, a really common pattern. Every time you're doing some efficient implementation of a data structure, you always pick some underlying representation tricks that should not be exposed to the client and are adding additional information for the purpose of efficiency. For example, when you implement dictionaries using a balanced tree scheme, the union function satisfies like no good properties. It's not associative, it's not commutative, even though clients ought to think that it is. So the reason is the underlying tree shape won't be the same. Basically, anytime you do any data structures, all the reasoning properties don't literally hold, which makes modular verification in dependent type theory a difficult challenge. So the goal that we're going to now think about is a notion of semantic modularity as opposed to a syntactic notion of modularity. So commonly, if you're used to using a language like ML, you're used to some tools for modularity being afforded using modules where you restrict what clients can physically see using something like existential types. And that's a syntactic discipline for separating information. But when you're doing verification, it's really important that you have a way of hiding information and proving semantically that you won't reveal it. That way, verification clients can see some of the information, but not all of it. So, okay, the big question that we're going to try to answer, in other words, is how can we reconcile modularity with verification? All right, so the first thing I need to tell you about as background is something called an abstraction function. This is something that Tony Hoare came up with back in 1972. I kind of spliced my own example into his quote. I hope that's okay. But he says, modulo this example, he says that for proving correctness of this batched enqueue implementation, you should define the relationship between the abstract space of list queues, in which list queues enqueue is written, and the space batched queue batch.x of the concrete representation. And you should do that by giving an abstraction function alpha from the batch queue implementation type to the list queue specification type. The idea is that you can't just verify batched queue's correctness on its own terms. You have to come up with some specification that clients should think about, which is list queue in this case. So once you give this abstraction function alpha, you have to prove a couple equations. So these are some commutative squares that represent equations. You should just think that if you go from the top left corner to the bottom left corner on either route, they should be the same. And the idea is that you have one of these equations per operation showing that the batched queue operations and the list queue operations are compatible up to this abstraction function alpha that converts you from the former to the latter. So in this case, for those of you playing along with this example, the abstraction function is this thing. Don't worry about the particulars if that's not something that you know about already. Okay, so back to these two clients from before. I want to point out that even though it wasn't literally the case that the two clients agree on batch queues, if you take out the queues that we were noting aren't literally equal and you apply the abstraction function, you end up with the same list that's just a singleton list containing the number 2. So in a sense, we want to verify not literally how these things are equal, but we want to verify up to the abstraction function alpha. So the principle is going to be, when you're doing verification as a client, you don't want to verify BQ's data literally, but you want to verify it at the level of LQ, the list-based queue specification, and you get there by using alpha. So this is the big idea from this work. We're going to try to build all three of these components into a type. And this sounds a little bit intimidating at first, but we're going to try to say, not only should your implementation type contain batchedq.x, that pair of lists type for efficiency, but you should also build in the specification type listq.x, and you should build in the transformation alpha that gets you from the implementation to the specification. So all this data is going to be built into a single type. And here's a quick diagram explaining what that means, but we'll get into more details shortly. The idea is going to be that on the left we have batchedq.x on the top and listq.x on the bottom with the abstraction function. All of that is going to fit into this hybrid implementation that I'll call blq.x for batched and listq type. And when you implement something like blq.empty from unit to blq.x, then that's going to, under the hood, consist of implementing batched queue's empty function on the top and list queue's empty function on the bottom, such that you prove that they cohere up to the abstraction function. So we're going to take this tall picture and we're going to compress it down a little bit, where we're keeping track of both the top and the bottom simultaneously. In other words, we mediate between implementation on the top and specification on the bottom. So okay, let me tell you how we're going to accomplish this, and we can make this a little bit more tangible. So we're going to use this thing called the abstract phase, which is a synthetic phase distinction. That fancy terminology really means I'm going to add a proposition to my language. So really, this is the only change I'm making to my univalent dependent type theory. By the way, we're there. So we're going to add a single proposition called abs that's supposed to tell you that you're in the abstract phase. So in other words, it means that if abs is in your context, you can't prove it in general because it's an abstract unknown proposition. But if you could assume if you assume that abs is in your context, you should think that you're only looking at the specification and you ignored implementation details. So for example, abstractly, which means assuming abs holds, then you should hope that the batched list queue implementation simplifies down to just the specification. So it ignores all those pesky implementation details. So again, diagrammatically, what this looks like is I claimed you were going to build batched queue and list queue and alpha into a single type. But if you assume this abstract phase holds, it's going to let you isolate just the bottom part. So it's going to let you isolate just the specification, which is good for verification. As we saw, list queues are well behaved for that purpose. So using this abs proposition, we can define two modalities. So we're importing these from prior work. I won't tell you the definitions, but they're not too bad. The concrete modality, which is this black circle, marks data as private, which means it's only important for efficiency reasons. And the abstract modality, which is this white circle, marks data as public, or available only for the purpose of verification. So using these modalities, we can mark the data we have with its purpose. So we can say that it's important for running the real code, or it's only important for verification. And using this construction that's called gluing, given as a special case here for this example, we can concoct this blq.x hybrid implementation. And here's how we do it. We say that batched and list queue hybrids consist of, an element of this type consists of a pair of a batched queue and a list queue, where the batched queue, you'll see, is annotated with that black circle concrete modality because the batched queue is the efficient implementation, and the list queue is annotated with this white circle because we're only interested in the list part for verification purposes. So we annotate each element of the pair with its purpose. And then there's a side condition where you have to make sure that up to some modal primitives, alpha of the batch queue is the list queue. So you make sure that the batch queue and the list queue cohere up to this abstraction function alpha. So in this way, we're building all of the data of the batch queue, the list queue, and the abstraction function into a type. You can see all three of those components in there. So what's good about this type is the following. Well, if we use the lemma that says that in the abstract phase, the concrete modality disintegrates, it turns into the unit type, and the abstract modality on the list queue evaporates, then you might notice that, well, abstractly, batched list queue turns into pairs of unit, which is because the batched queue type under this modality disintegrated down to the unit type. And the second component just consists of a list. So really, I'm storing pairs of units and lists, which up to a notion of equivalence is just the same thing as storing a list. So in this way, we're able to concoct this type blq.x that achieves the intended goal. It's a hybrid of batch queues and list queues, such that if you want to isolate the specification part for verification purposes using the abstract phase, it does indeed degenerate to lists. Okay, so let's think about how you'd write code on this thing. In particular, let's try to do the simplest possible example of batched list queue's empty function. So empty is going to be a function that goes from unit to this hybrid BLQ type. And just let me expand that out. That's the same thing as we had on the previous slide. The way that I'll implement this is by giving a pair of a batched queue and a list queue. And in fact, I'll just use the batched queue empty and the list queue empty that come equipped with the batched queue and list queue implementations. So I do have to mark both of these with their appropriate modal primitives, but anyway, that's just making sure that things type check. That's making sure that the annotations indicate whether something's important for efficiency or for specification. So once I pick this pair, there is this side condition that means I have to show that these things cohere up to the abstraction function, which if I just plug those things into that equation, says I have to verify this, which, okay, simplifies down immediately to this thing. And you might notice that there are some modal primitives on the outside, but it would suffice to prove this by using congruence with respect to those modal primitives, that you just have to show alpha of batched queues empty is the same thing as list queues empty, which is in fact exactly the square that we started off saying is part of an abstraction function verification. So we already proved this, and we were able to assemble the data of batch queue empty, list queue empty, and the proof of coherence into this one operation. So this was the intended goal. I won't show you the other operations, but they're pretty similar. So what's the payoff of this? Why did we do all this? Well, we get a principle of non-interference, and this is something that was anticipated by Dijkstra in 1965, if you can believe it. So Dijkstra back then was thinking about the principle of non-interference, as he called it, which is that the correct working can be established by taking into account the exterior specification only, and not the particulars of the interior construction. Here we're calling exterior abstract and interior concrete. So, by the way, this notion of non-interference in our work we observed is the same thing as an information flow kind of non-interference, which is an amazing confluence of terms. So let's see what this looks like in practice. If we define queues, finally, by the way, at the beginning I defined this interface to be pre-queues because there was no restriction that these things behaved like queues. But in reality, we want to restrict these pre-queues such that they behave like queues. And we can do that by considering all of the pre-queues that abstractly are equal to list-based queues. So this gives us a notion of pre-queue that actually has the intended semantics. We can note that, for example, batched list queue hybrid has this interface because indeed, as we showed just a second ago, abstractly it's the same as list-based queues. So now if we bring our clients forward from way back when, and we have them take in queues rather than pre-queues, which come with this restriction that abstractly they're known to be list-based queues, we can prove the following theorem, which is that, in fact, it is true that for all implementations of the queue library, abstractly, C1 and C2 agree. And the proof is a little silly. I included it on one line. It's really just any possible implementation of queues is abstractly list queue, by definition. So if we restrict the intended semantics to be list queue, which we can now do using this abstract phase, then this principle of modularity falls right out. So we reified this principle that Dijkstra was hoping for as a theorem. Okay, so this not only applies to the situation of usual dependent type theory verification, but it also upgrades to cost analysis. So even back in 1995, Stepanov, who developed a lot of the C++ standard library, was thinking about modularity and its connections to efficiency, where he was saying that you can't have interchangeable modules unless the modules share similar complexity behavior. So you have to have complexity assertions as part of the interface. The idea being, if you had one module that was very efficient and you swapped it out for an inefficient one, surely that's something that a client would notice, and therefore it's a little bit anti-modular. So if we want to think about such things, we have to switch to a dependent type theory that enables cost analysis. And that's something that my group has been working on for the past few years. So we have this tool called CAF, which is a dependent type theory for cost analysis that includes a monadic cost effect, which is written as charge C. That just means adding C units of cost to a program. So in particular, you're able to return values into this monad, and you're able to charge C on top of something that's already monadic. And we also had this thing a couple years ago at POPL called decaf, which extends CAF with inequality of costs as a simple directed type theory, where inequality means, well, E is less than or equal to E prime when E and E prime share the same behavior, but E might have lower cost than E prime. So that's your one-slide introduction to our past few years of research. Okay, if we add this monad on the output of the pre-Q operations, so you can have effects in empty NQ and DQ, we can now annotate batched Q so it actually has cost. So we can pick a cost model to be the number of cons nodes created. Here we'll therefore charge 1 on the NQ function because we always create a new cons node. And DQ, we will sometimes charge 0 in the common case, but occasionally in this expensive case, we'll charge linearly much cost because we have to create new cons nodes when reversing the list. So now it remains to annotate list-based queues so that they can match the batched queues in order to complete this analogy with the previous work. So if we had to come up with some list queue that matched batch queue, some public-facing specification that included cost, well, I guess you can just pick that the cost of list-based NQ should be 1. So list queue is now serving as some sort of cost-aware interface for batch queue. And in fact, this equation will hold if you pick 1 because the batch queue always took 1 cost on NQ. What's the situation for DQ though? Unfortunately, we can't always know what the cost of a DQ is going to be because sometimes it's 0 and sometimes it's linear depending on some internal implementation details that we can't possibly see at the level of lists. So what we can do is we can pick an admittedly pessimistic upper bound by picking linear cost for DQ and saying that this square laxly commutes with this inequality. So if we can build in this notion of inequality, then we can represent upper bounds as cost interfaces. And this is extremely important because basically all the time, once again, if you ever implement a data structure, under the hood, the cost will be something that you can't literally export. Any kind of data structure uses some private implementation details to incur cost, and you can't tell exactly how much from the implementation. Always you have to give some upper bound. So in order to include these squares with inequality, we introduced this novel ceiling effect. And ceiling lets you combine two programs such that you abstractly pretend you're the upper bound, but you also keep track of this implementation that has the intended cost. So here, you can seal some program E against some program E sub circle, where that's the abstract upper bound. And as long as you prove that they're upper bounded, you can consolidate these things into a program that represents them both. So for example, if you had this inequality square where the top edge, the real implementation was costing 2, and just as a contrived example, the specification wants to upper bound that with 3, then you can write this example program by sealing 2 cost with 3 cost. So there's now the question of how you would do this in the bigger case of batch Q DQ being upper bounded by list Q DQ, and morally you just bound batch Q DQ by list Q DQ and seal them, but actually there's some more complexity going on there. This doesn't literally type check, so see the paper for more details. All right. So let me conclude by first saying what we did in this work is we used 4 key techniques, which are univalence, synthetic phase distinctions, modalities, and CAF, to talk about modularity, including cost. And of course, we're building on a mountain of related work. I can't talk about that at this level, so please see the paper. We have a whole comparison, but we build on a long tradition of modularity, and we have really cool connections, I think, to a lot of prior work. So let me summarize what we did. We noticed that we can represent abstract models and abstraction functions inside of types, so we can not just choose the efficient implementation type, but also some other aspects for verification. And that lets us realize these verification level properties And it gives us a notion of semantic modularity, where you have to prove you don't reveal too much information. And this is, by the way, a pretty unobtrusive change, because all you had to do was postulate a single new proposition in your type theory. So you can use this today. In fact, it's implemented in cubical agda in our artifact. Once we had this abstract phase, we implemented a little standard library based on prior work, which is the concrete and abstract modalities and gluing, which let us cook up this hybrid implementation. And then from that hybrid implementation, we noticed that we got a non-interference and modularity principle, which is not just a principle like it has been historically, but a provable theorem that's part of our standard library. And that gives you a notion of modular verification. And finally, we extended to the domain of cost by allowing you to upper bound an implementation by a specification using this ceiling effect. All right, well, I think that's all the time I got, so I'm happy to take some questions. Thanks.
So would you say a few more words on how univalence is used in your stuff?
Yes, so you might have noticed that I said BLQ is equal to LQ. And of course, that's not literally going to be true. That's going to be some kind of univalent equality. So you can prove they're equivalent, but it's, yeah, you're using equivalence. We also use the structure identity principle to replace batch list queues with list queues, for example.
That's very nice. I come to it from the context of having spent way too long writing abstraction functions from bits of systems C code to specifications in other ad hoc, nicer languages. And it's kind of obvious after doing that for a while that it would be nice to have tighter connections between these things.
Yeah.
So I spent the whole talk trying to understand whether conceptualizing in terms of some integrated language with modalities for a phase distinction would help, or how it would help, and I don't understand.
Yeah, so I guess we're trying to accomplish exactly what you described, which is take all of these abstraction functions that have been verified over a long time and consolidate that data into a uniform type theoretic framework that affords you principles like modularity. So when you build the abstraction function into your type theory, then you're guaranteed this notion of non-interference and modularity that we looked at, because you are treating this abstraction function as a distinct first-class object. So rather than just another function, it's built into your type. And the fact that it's connected with this abstract phase proposition lets you guarantee certain modularity principles. So it's a way of building all of the data that we have before about abstraction functions into the language in such a way that affords these principles.
Distinction is kind of built into the ad hoc separation between two different languages that's common in verification tools. So
Let's take it offline, because we have lots of questions.
Sure, very nice talk.
Thanks.
I'm wondering about amortized costs, because that's really what you're getting from the queue, right?
Yep, so admittedly, I picked a pretty pessimistic upper bound, but our upcoming work is about building this up to amortized interfaces. So I'll have to ask you to stay tuned for that, but I think we have something cool.
Yes, very nice talk. I'm wondering whether this would work if you, rather than had abstraction functions, used abstraction relations or something a little bit more flexible.
Great, so that's a good point. This does work with relations. There's kind of a directedness to it, though. So you always do, at least we observe in this work, it seems like you always want to have some kind of directedness where you can take something concrete and make it abstract. If you happen to have two concrete things that you wanted to relate, one way that you can do this is by connecting them both to some common target. So if you had batched queues and then, I don't know, real-time queues, then you could connect both of them to lists, and the relation between those two things would be that they map down to the same list abstractly. And you can always do this. If you have any relation, you can always construct some abstract model that they'll share by taking like the push out of the relation. So you take, well, whatever. There's some construction you can do to make this fully general, but this is compatible with relations. Is that good?
Okay, let's have the next speakers set up, and we have time for one or two more questions.
Thank you for the talk and the example that you gave of the worst case complexity. It just so happened that the complexity you gave was also the one of the concrete list specification.
That's true.
Is this a restriction, or would it be possible to give a lower cost there, which is not fulfilled by the specification?
Yeah, so you can definitely give a lower cost. I picked this batch queue example just because it's easy to talk about at the level of this talk, but there's no requirement that the model coheres with what the list is doing in this example. It just so happens that we had a coherence there. But as another question asked, you would probably want to say that the batch QDQ has constant amortized cost anyway, and modulo the fact that we don't have amortization in this work yet, you could totally say that it has constant cost. It's just...
Well, I was more thinking of a case where the specification has, for example, in your case, linear complexity, but we know that there is an log n complexity for an actual good implementation. And then we would want to say, well, it's easier to think in terms of lists, but in actuality, we want something that is logarithmic.
That's exactly what's happening here. So the annotations you put on the specification are usually not realistic to the specification code. So you should think of the specification like math that you're using for analysis purposes. So if you had some log n implementation, you can still annotate the list-based specification with log n, even if that's not a realistic cost model, because you should only be putting a realistic cost model on the implementation, not necessarily on the spec, which is just math. Does that make sense?
Thank you.
Thanks.
Okay, next up, Vova is going to tell us about foundational multimodal verifiers.
Hello, everyone. Thanks for coming for this talk. I will tell you, I will tell you about our work in National University of Singapore. We've been working on foundational multimodal verifiers. Some of our verifiers you might have already seen earlier at the conference. We had 2 talks on Daphne workshop about Velvet and Whale, and then later on Monday, George and Chuan had an amazing tutorial on Whale. So now I will tell you a little bit more about foundations of those tools. What do we build them on top of? Well, given that you are here on this talk, I assume you are interested in program verifiers, maybe even in automated ones. We all know about Daphne. Parus, of course, is very popular now. Viper, with Cobra and Prousty and other things. F-Star, Liquid Haskell, GML, Boogie, Tamarin, Proverif, and so on and so forth. So there are many, many of them. That's not even the half. And even though there are so many of automated program verifiers, usually they share something in common, like POP pipeline. Well, it's pretty easy. You give them the program and the spec, and then they do some magic and transform it to verification conditions, some formulas, which kind of correspond to the correctness of the program, send them to SMT, and then if you're really lucky, then it will say, yes, everything is great, you can chill now. If you're a little bit less lucky, but that's still a great outcome, it will disprove your spec and give you the counterexample. And it's great because you can use this counterexample to refine your program and your spec. But it's not all milk and honey. And of course, oftentimes, if your specification is too complicated, if your program is too large, they can just time out. And if you have experience with using such things, you probably know that in this case, it's really hard to progress and debug what has actually happened. The verifiers which do not suffer from this problem are interactive ones. Usually we'll build them on top of ROC or Isabelle or something else. And I'm talking about VST, Iris, HTT, stuff like this. Well, working with such verifiers is, of course, very intellectually fulfilling, and it helps us publishing POPL papers, which we love. And, but using them in practice might not be exactly the most economically efficient strategy, because the cost-benefit curve is not that great, right? You will spend a lot of time setting up definitions, proving auxiliary properties, and you will only get some result which you can show to someone, maybe your investors, towards the end of your verification effort. And so now if you want to boost the benefit on the early stages of the development, you can use bug-finding tools. I'm talking about quick check, like property-based testing, maybe model checking, fuzzing, and maybe something more symbolic, like infra-pulse. So bug-finding tools. And more or less, this is it. This is the state of the art. You can kind of split it in 3 groups. Automated symbolic verifiers, interactive ones, and bug-finding tools. And, well, as the slide suggests, we want to target the middle ground. We want to do so-called multimodal verification. So that means that we want to combine the capabilities of all different provers inside one tool. And we want to build those tools for each domain-specific problem. OK, what's the recipe? How do we even approach building such multimodal verifiers? sorry, I forgot to mention that these tools, they should, when you start prototyping your system, you should be able to catch the shallow bugs using proof finding techniques, then go on and try to prove something about your program automatically, and only if this fails, you should be able to like smoothly transit to interactive proofs. Okay, now, how do we build such tools? When you design a verification framework, there are certain design aspects which you can implement in different ways. I'm talking about program effects, for example, state, termination, exceptions, and non-determinism. Of course, there are much more, but we will focus on these ones. And combining the different treatments of those effects in different combinations will actually give you tools from all these different groups. Let's look at some simple examples. Daphne verifies programs symbolically, so it's a symbolic state. By default, it checks the termination, so it's total. Then also it will try to make sure that your program doesn't have any failures or exceptions. And also whenever you have some non-deterministic choices in Daphne, then it will try to verify your specification for all possible choices, right? Now if we look at VST, VST is by default is partial. If we look at something like infer, then the idea is there is different. It will actually try to find the non-deterministic choices. It will try to find a trace of your program which leads to something bad, like exceptions. And if we talk about property-based testing, then you will try to do the same thing, but instead of using symbolic methods, you will be doing this by executing programs. So concrete methods, right? And in our work, we present Loom. Loom is a system which helps you building verifiers, combining the capabilities of all these different tools from different groups. How we do that? Well, we make it kind of easy to make these different treatments of effects as parameters. So basically, the tools which we build on top of Loom are multimodal verifiers. And now you might be asking, how do we combine, for example, interactive proofs and automation? Well, the answer is on this slide already. We built Loom on top of Lean. Because in Lean, you get a very nice way to kind of mix interactive proofs together with such powerful automation like SMT and with proof reconstruction or grind and ASOP. And of course, let's look at this simple example. We will be now building with you a verifier which reasons about money managing programs. It's called Kashmir because, well, it's about cash. And we will go through all these effects one by one and start with state, of course. Again, Kashmir is all about money flows, withdrawing money and depositing money. And we also built on top of Loom. That's why it kind of makes sense to assume for now that the programs that we are going to verify are just stateful programs with state being a balance, which is just an integer. And the very first program that we will verify is a simple withdrawal function. It takes the amount that we want to withdraw, then it gets the current balance and updates it. Well, nothing too complicated, but of course you don't want to show user all those like monads, right? They want to see kind of imperative style code. And luckily with great support for metaprogramming in Lean, using this small metaprogram, we can glorify our code to make it look now more like imperative program where basically balance now is just like a global variable which you can modify in your function. So this is a front end of our verifier. And even though with this front end it looks fancy, it is still monadic code. So we can execute it directly in Lean. And with this, you can bridge the gap between all these lightweight bug finding tools like model checking, fuzzing, or property-based testing, basically just implementing them in Lean directly using the execution. And we did it for our verifiers. Now, if you want to start the verification, of course, the first step would be to add postcondition or precondition, so basically add specification. And Loom gives you tooling to amend your front end with specifications. Well, also it gives you the commands to verify your programs. Let's zoom in on this command a little bit. So what do we need to do to enable this tooling from Loom as designers of the verification framework? Well, we have to do two things. First, we have to fix the assertion language. In this case, just predicates on the balance. And second, we of course have to define the weakest precondition calculus. Nothing too surprising. Of course, we'll have to prove some properties about our weakest precondition calculus. But for now, let's for now forget about it, and I will show those properties a bit later. And once you did all of that, you will get two things. First, you will get the proof correct command, which will, given your program, define, based on your specification, the lean statement in terms of the Hoare triple, which is just a weakest precondition in disguise. And second, it will give you tactic to basically prove such things. So how this tactic works. Exploiting the properties of your weakest precondition, it will generate you a bunch of formulas, as a lean involves, verification conditions. And then, using the automation of your choice, it will try to dispatch all of them one by one. And now, if automation fails and some goals cannot be dispatched, just like easily with SMT or any other automation you picked, you can go ahead and prove things manually. That's how we kind of bridging the gap between automated verification and interactive one. But that was all pretty easy. That was an easy program. Let's go on and verify more complicated programs with loops and see what we do about termination. This is the program that we will verify now. Instead of having only one amount to withdraw, it has the whole list. And, well, the specification is amended. Now we want to make sure that the new balance plus all the things that we have withdrawn equals to the old balance. And we will implement this program simply by, while we still have something to withdraw, like deducting it from our balance in the loop. Looks not super complicated, but of course it has while loop, and lean as a total language doesn't accept arbitrary while loops as long as you work in just state monad. Well, in lean, there is a nice workaround. If you extend the programs that you consider to basically now state transformer with option in the bottom, then you can have arbitrary while loops. So I won't get into too much details, but the idea there is that the semantics of the divergence is just option.none. And now, if you want to reason about these programs, then we first have to, of course, provide the invariant. And second, you might be asking, oh, is our logic partial total? Do we need to provide decreasing clauses or not? Well, the answer is depends. It depends on this option. Remember, I said that the semantics of divergence is option.none. So depending on how you define the weakest precondition on this option, you will get different logics partial total. If you, for example, define it to be true, then you get partial logic. Otherwise, you will get a total one, so you will need to provide the decreasing clause annotations. And in Loom, we can simply control it by setting the specific option semantics determination to either partial total. Now, side remark. Of course, the partial correctness, the total correctness proof is more involved. You have to now decorate your program with all the decreasing clauses. But of course, it will also give you more guarantees. So we have you can do like very simple meta theory proofs. We give you lemmas on the level of Loom to prove that if you have a total correctness proof for your program, then it will never give you option. It will never give you none. So you can always extract the value. Well, now let's add even more stuff to the programs that we consider. For example, if we try to withdraw something that is larger than our current balance, let's throw an exception. Makes sense, right? To do this, we will have to amend the class of programs that we are looking at and add the exception transformer on top. And also now, just for the fun of it, instead of passing the amounts as the argument, let's model kind of input-output with non-determinism. We will be non-deterministically picking the amounts that doesn't exceed our balance and just withdraw them in the loop in the same way as we did. So to do that, we of course will have to add the non-deterministic monotransformer to our monostack. And if you want to verify this code, you will have to do two things first. You will have to say what is the semantics of your non-deterministic choice, demonic or angelic, and you will have to say what is the semantics of the exceptions. Well, we will start with verifying very conventional property. We will just prove the functional correctness for all possible choices and also make sure that your program never throws an exception. To do that, we will have to, of course, choose the demonic semantics for the non-deterministic choice. In this case, it just means that weakest precondition of the choice is for all quantification. And for the exceptions, we will have to choose the failure semantics. So weakest precondition of throw is just false. Now, if you try to verify it with loom solve tactic, it will basically verify your program. And on the meta-theory level, that means that you have proven that your program never throws an exception with total correctness. So you just have proven the absence of bugs. Now I will show you how, tweaking the semantics of these effects, you can also prove the presence of bugs. So do bug finding. First, let's introduce a bug to our problem. It's easy. Instead of choosing the program amounts non-deterministically, we will choose the arbitrary one. And now, of course, this exception can be thrown. Let's try to prove it. Well, first thing, we will have to change the semantics of non-deterministic choice from demonic to angelic. So weakest precondition of throw is now exists. And we have to change the semantics of exceptions from false to true, because now we want to kind of get them right. And this, together with changing the specification to false, will mean that you can only verify your program now if it throws an exception. So if you run loom solve tactic now, it will verify the program. On the meta-theory level, it will mean that there exists a trace in your program which leads to an exception. And you have proven the presence of bugs. So this is more or less everything about the tour of Kashmir. And here I would usually just go and list the list of contributions, but, well, given that's a POPL, I feel a slight suspense in the audience. You might be wondering, well, isn't it just the extra monads? Come on, we have bazillion papers on the extra monads. Why do we need one more paper about foundations of the extra monads in POPL'26? Well, loom is not exactly the extra monads. This is the extra monads plus one more thing, which we call ordered monad transformer algebra, and I will try to explain why is it useful. To do that, let's backtrack a little bit and imagine we want to verify arbitrary program, and we want to do it with the extra monads. So what we will have to kind of instantiate? We'll have to give the weakest precondition calculus. We'll have to prove 3 laws. We have to prove that it respects pure bind and also is monotonic. You will also have to define the SMT-friendly definition of, give an SMT-friendly definition of Hort triples in an ad hoc way. And also, you will have to compute the weakest precondition for basic computations like set and get and state monad or lifted computations. And then you get push-button automation. Now, even in this small example, we had to change the monad stack at least 3 times. Does it mean that we also always have to provide new WP and prove these properties over and over again? And that's exactly what Loom helps you with. In Loom, we not only automate the program verification, which arguably has been done by the extra monads 10 years ago, but we also help you, we simplify the process of construction of automated verifiers. How we do that? Well, we introduce this notion of ordered monad transformer algebra, which is the structure on top of your transformers. And I won't explain you what exactly is that. You can read the paper. But it has one nice property. If your monad is application of a bunch of transformers, for each of which you get this instance of this ordered monad transformer algebra, then you can combine them in various ways. But we will be automatically deriving a weakest precondition with all these nice properties for you. Yep. So, and this is it. This was Loom. Loom is designed to build foundational multimodal verifiers, which are sound by construction. We do proof automation using the extra-monad techniques. We add this ordered monad transformer algebra on top to automate the verifier derivation. And also, we build on top of Loom to enjoy all these nice pieces of ecosystem like lean SMT and lean auto to translate goals to SMT and get the proof reconstruction. We enjoy the plausible, which is the lean way to do property-based testing MATLib to get all the formalized math and so on and so forth. And we built 2 realistic verifiers. One of them is Whale, which is the verifier for distributed protocols. And another one is Velvet, which is the verifier for imperative programs. Well, Daphne-like verifier. And now this is it. Thank you very much. I would be happy to take questions.
Thanks for the talk. In your example of finding bugs, you prove that there exists a bug, but do you get a counterexample that you can use to fix your program?
Oh, you mean the counterexample of the example of an input where we throw the bug?
Right.
Okay, we don't have the functionality on the level of these proofs now, but we get it at the current stage. We get it from the property-based testing. So we also have, for example, for Velvet, we have the property-based testing harness, which will kind of give you the inputs for which your program leads to a bug. Yeah.
When I see the word automate, I think it can either mean you have a nice theory that like by construction gives you sound verifiers, or you have a bunch of tactics that do sort of optimistic metaprogramming, and when you're lucky, you get a sound verifier. Which one is this?
So this is a combination of both. We have a nice meta theory, which basically means that you have to define less things and prove a little bit less properties. And you also need to do it for each particular transformer. And also we have all these kind of meta programs that using this meta theory will derive the weakest preconditions that you are interested in. So this is kind of garbage in, garbage out principle. We want to derive weakest preconditions such that if you had first order specifications, then your verification conditions that Loom generates is going to be first order as well. And we achieve this by combination of both, yeah.
Yeah, thanks. Really interesting stuff. So when I saw this this monad transformer ordering, I don't know how you called it. I mean, I probably have to read the paper to understand exactly what it is. But the issue of having to reorder the monad transformers sounds like what effect types usually are meant to solve. So would effect types also solve the issue that this transformer thing, reordering thing solves, or is there something fundamentally different here?
Yeah, I'm not sure what exactly, what is the thing that you...
Effect types.
Effect types. Yeah, I'm not, yeah, we should, yes, we should maybe take it offline and compare because I'm not entirely sure.
Okay, thanks.
Yeah.
Thanks for the talk.
Yeah.
I have a question maybe related to the previous one. Right, so you showed that if you have like an arbitrary nesting of monads, you get the weakest proof for free.
Yes.
And then you had the example where it was like state of non-det of option or something. Does Loom also help me figure out which monads I want in there and in what order?
Sorry, can you repeat?
Does it also like help me figure out that I want like non-det and state, or maybe I want state of non-det? Like.
Oh, no, yeah, not really. Yeah, you have to just set up what effects you need. You kind of construct a monad yourself, and then for this monad you will get weakest preconditions. Yeah, but that's an interesting direction. Yeah, maybe we should look into that. Thanks.
Thanks for the talk. When you switch to a non-terminating programs, you can, so you're going to the option monad, but also you're elaborating to something that is fueled, right? That the BDEF is doing a kind of elaboration of your initial program to something that is now fueled and returns into option?
Yeah,
deeply embedded?
So the way we go is basically we do shallow embeddings, and then depending on what type you want to get in the end, what type of programs they want to get at the end, you will get elaborations to kind of all these different monads. Yeah.
Hi. I should.
Yeah.
Are you done or?
Yes, go ahead.
Okay.
Last question, you got 1 minute.
First of all, very slick talk, great talk.
Thanks.
If you were to use separation logic with Loom, would you have to rewrite anything? Do you think it would just fit in the framework?
Yeah, that's a great question. We are working on separation logic, and we think you can fit it into the framework. And we have some, like prototypes. Maybe we can take it offline. I can show you something.
Thanks.
Yeah.
Okay, let's thank the speaker. All right, next up, Ren King will tell us about stateful differential operators for incremental computing. Take it away.
Thank you for the introduction, and thank you all for coming here. And my name is Ren Qing. I'm a PhD student from KIT. And today I'm going to present our recent work on incremental computing. And this is a joint work with my supervisor, Sebastian Etwek. And so at first, I want to introduce what is incremental computing. And in a nutshell, it's just a technique that allows us to do efficiently updates the program's output by the program when the input changes, instead of doing full scratch recomputation. And usually, an incremental computation has two phases. And the first phase is called initialization, which is like a normal program takes an input and maps it to an output. And after that, whenever there is a change to the input, the incremental computation will apply a slightly different strategy to update the program's output by the program input changes. And this process will just repeat every time the input changes. And there has been a lot of research has shown that incremental computing can be asymptotically faster than recomputation, and also usually the user can observe a 10x to a 10,000x speed up in practice. And I know that all of you here may come from different areas and to draw interest. So I listed some our daily using tools at here, which somewhat supports incremental features. For example, the IDEs sometimes support incremental type checking or incremental program analysis tools. And databases supports incremental queries. Even for SMT solvers, we can configure it to run incrementally to push or pop assertions instead of rerun the full checking. And so, as I said, incremental computation will apply a different strategy to update the program's output. So now I'm going to just introduce two primary approaches of incremental computing. And the first approach is called selective recomputation. And the representative of this line includes self-adjusting computation or incremental build systems. So the basic idea of this approach is to reuse the previous sub-computation results if the input to this sub-computation is not changed. And to show you what I mean, let's just quickly to consider an example of a string processing task. And as you can see, this is the diagram of this computation, which takes two strings as input. And on the bottom branch, we take a username Alice and apply the operator to uppercase to convert it into the capital case. And in the bottom branch, we take an email address and using to lowercase to normalize this email address to a lowercase. And finally, we take these two intermediate results together to get the final output. And now let's consider how the selective computing works if we just modify the second input by inserting a character G before the mail. And I have highlighted that here. This is a change to the input. This is a very small input change. And the incremental computation detects that, okay, since the first input is not changed, so we can directly reuse the result of to uppercase, which just take constant time. But since the input to lowercase is changed, so it has to do a full recomputation, which takes the time proportional to the second input size. And also, since the input to concat is also changed, we also have to perform another recomputation about concat to copy the first part into the final computation, so it also takes the time of big O of the size of the first input. Note that I just consider the string as a linked list in this talk, which is very common in functional programming languages. And so as we have seen it here, even we simply insert one character to the input, the cost of updating the output will take the time proportional to the original input size instead of the change size. So this naturally just leads us to the question, can we do a better job? So to find an answer, let's just shift our attention to the second interesting incremental computing approach, which is called differential updating. And the representative work in this line is incremental view maintenance, which is actually the core technique for incrementalizing database queries. And the basic idea of differential updating is to utilize the change values and to just build the incremental computation by chaining differential operators together. And the differential operators are the operators does not map values to values, but from value changes to value changes. And let's just go back to our original example to show how the differential updating works. So the first step to use the differential updating is to define what kind of changes can we apply to a value. And here I just define two types of general changes to a string, which is either an insertion at a given position or deleting some characters from a given position. And let's go back to our example. As we can see it here, in the top range, since we did not change it, so I just put an empty insertion at here. But for the second input change, it's just insert the character G at the index 7. And so as we can see it here, the efficiency of the differential updating approach really just depends on the efficiency of the differential operators. So now let's just investigate them case by case to see whether they can bring a better speed up. So let's start from a simple operator to uppercase, which just converts all of the characters in uppercase. And now we do a case analysis on the changes. So now let's think about what will be the output change if we change the input to uppercase by inserting a string. I think, so as you may have come up with that, it just for the effect of this input change just to insert the uppercase of this string to the output. So for deletion, it's even simpler because it's just index-based. It does not talk about the content. So we can just, and also to uppercase does not change the length of the list or something else. So it's just propagate this change. So from this example, we have already seen that the time complexity of delta to uppercase will just be proportional to the change size instead of the input size. So which means that we can get a symptotic speed up if the input change size is smaller, very super smaller than the original input size. But now let's consider a more complicated example of the concatenation. And the concatenation just concatenate two strings together. And we think, and for simplicity, let's just think about what will happen if we change the second input by inserting a string. So the result is because the second input will be shifted by the length of the first input, so the output change of this insertion will also be shifted by the length of the side of the first input. And for deletion, it's similar. We also need to shift the effect by the length of the input. And I use the green color here as shown here. It's a kind of wasteful to recompute the length of S1 all the time. So, so why not we just remember this information when we use the delta concate operator, then which allow us to get the output change in constant time. So it's actually a symptotic speedup I have observed here because usually the concatenation, if we do recomputation, it's linear. It has this time complexity is linear with the size of the input. Yeah, no, if we only consider second input change in this case. So if we come back, we can observe that if we use the differential updating approach to incrementalize this computation, we finally can get the time complexity will just be proportional to the change size instead of the input size. And so this is actually a more effective approach for incrementalizing some computations. But so far, actually, there are two limitations of this approach. And the first limitation is that before our work, only the efficient differential operators only exist in the domain of databases. For example, selection, union, join, aggregation. Also, actually now, as you have seen, the states actually play a very important role for efficient operators. But currently, there is no framework for designing and verifying such custom state differential operators. And this is just the starting point of our work. We want to develop a formal framework for developing and verifying differential operators that can utilize custom states. And we formalized this framework in ROC because I have not shown that here, but actually these custom state operators are very error-prone. So using ROC can ensure that all of the operators derived from our framework must be correct. And okay, in the rest of this talk, I will just go into some details of our framework. And the first thing I want to introduce is change structure, which defines the algebra of changes. And I use the ROC syntax that here we define it as the type class, takes two type parameters as the type parameters. T is the value type, del T is the change type, and the patch function takes a change and a value and gets an updated value. And we see is a binary relation, which intuition is to specify what kind of changes are valid to a value, or what kind of changes will not cause default behavior of patch. For example, if we patch a natural number 1 with a -2, then it is default behavior. And usually these default behaviors are very dangerous when we start to do verification. So when we implement the change structure, we require the users to provide a valid condition relation. And let's just go to the change structure on strings, which we have seen part of it. These are the possible types of changes to a string, insertion or deletion. And now we can define the patch function for for updating the string by the changes. And finally, this is the new part where we specify a valid condition for the string changes. As we can see here, if that's an insertion change, we must require that the starting point of this insertion do not exceed the range of the string. And also, if we perform a deletion, we must ensure that all of the delete characters also stays in the string. And okay, and from these basic change structures, we also can build higher order change structures. For example, one very common change structure is for pair. Because sometimes the operators have more than one parameter. So we have to have some change structure on these multiple values to specify what kind of the change structure for the input of operators. So in our framework, the change structure for pair consists of 3 types of changes, either change the first value or the second value or both of them by utilizing 2 basic change structures, C1 and C2. And also we have change structure for option values to, for example, turn a non-value to a sum value and use a change to turn a sum value to another sum value and also turn some value to a non-value. And also we have the change structure for patching sequential changes because sometimes it's hard to express a change using a single descriptor. So it's also very often used when designing differential operators. Okay, so far I have not talked about the correctness of differential operators, but it's actually very important because differential operators are basically want to use a smart way to update the programs, which has a lot of edge cases. And so let's just have a look at this diagram. We start from the 2 uppercase. First we have an initial computation that maps the input to the output. And then we also have there is an input change delta in, and we utilize the delta to uppercase and get the delta output. And so the question is, how do we know that the delta out is correct? And to do that, we can use a commutative diagram to show the correctness. And to check if delta output is correct, what we can do is to first use, if there's a change structure for the input type, we can get the updated input by using the patch function, and then apply the to uppercase to the updated result. And also, if we found that if we use the updated output to, if we use the output change to update the output, and the value is the same as do a recomputation from the updated input to the output, if the diagram commutes, then basically we can say that the delta to uppercase does a correct job. And so now we use the ROX module system to translate this diagram into the formal specification, and we start with stateless differential operators like to uppercase. And in this spec, we first require we need to provide two change structures for the input type for the output type to allow us to patch the values. And also, we need to provide a basic computation function and the stateless differential operator to map the input change to output change. And to prove this delta F is correct, we need to we have two axioms. The first axiom is that, okay, if the input change is valid, then the result of doing a recomputation using F is the same as updating the original result by the output change produced by delta F. This is also known as from scratch consistency in the terminology of incremental computation. And also, since our scenario is to connect a lot of these differential operators together, so we not only need to require that the input change is valid to the input, also we might connect this operator's output change to the next differential operator. So we also need the output change is still also valid to the original output value. And for string differential operators like string.length or to uppercase to lowercase, we all can model them as stateless differential operators. And now let's consider a harder case for stateful differential operators. It's a bit different because now we need to use states. And where the state come from, it's in our specification, it will come from the initialization. So if we were to use concat, and then in the first step, we first not only map the input to the output, but we also get an initial state, which we can use to efficiently react to the input change to get the output change. But more importantly, we also need to update state. And this process will just repeat and so on and so on. And so let's, after we know how the stateful differential operator works, let's have a look at the formal specification. And so the first part is still the same, the change structure for the input and output, and also the initial computation function. And the next part is more crucial. We need to provide a state type, and also init function that initializes the state from the input, and also a delta st function which will take an input change and the current state to get the update state. But now I want to hold on for a second, because if we observe the signature of the delta st, it might remind us about the signature of the patching function. So that means that we can perfectly using the change structures to quantify the behavior of delta st. So instead, we just require the user to provide a change structure between the state type and the input change type. And also, for verification, we must specify what is the correct state, which we just put an invariant here. I know in the first talk, there is more interesting ways to verify the internal state is correct, but here we just use a customized binary relation, which is very general. And also the next part is about the stateful operators and its correctness. So at here, the differential operator takes the input change and the state and the get output. And so the valid property says that is the same as the valid for stateless, which I just neglected here. And the correct means if the input change is valid and the state is correct, then the output, then the from scratch consistency still holds. So this is not the end, because we now also need to make sure the state is always correct in the lifetime of this operator. So the init says that the initial state is correct, and the in step says that if the current state is correct, then after updating the state, it is still correct with respect to the updated input. And to explore the expressivity of our framework, we did several case studies. The first one is we used our framework to model and verify a bunch of novel string differential operators which do not exist before. And for example, we model is empty as a stateful operator which takes the length of the string as a state, which allows us to find the output change in constant time. And also for index of and last index of, we use the original input value and output value as a state, which allows us to update the output in the time proportional to the input size in most cases. There is only one case where if you delete the occurrence of the thing you want to find, you have to do some recomputation. And in the second case study, we also start to use our framework to model existing differential operators in relational algebra domain. For example, we modeled an incremental aggregation algorithm as a stateful operator in our framework. This kind of incremental aggregation is used a lot in the incremental program analysis in this real-world projects. And this is also the first mechanization of this algorithm in ROC. And we also have successfully modeled the database differential join operator as a stateful operator in our framework. This shows that our framework is capable of modeling existing complicated operators and also is able to model novel operators to push this differential updating approach to the general domains. And what we also did is to extract this raw code to executable the OCaml code and build several benchmarks to test their practical performance. For example, this is the first one, which it consists of 2 selection operator and 1 drawing operator, and finally we do a max aggregation, and we just randomly put in union changes or deeping changes to this computation to test its performance. And what we have said here, this is the benchmark result, and the y-axis is the execution time, and the x-axis is the input size, and the blue line is the recomputation execution time, and the orange line is for the incremental computation. So lower is better, and we can observe that the differential operators can bring asymptotic speed up. And also another benchmark is about string processing, which consists of operators like to lowercase and to uppercase, and we also can observe a significant speed up at here. So to conclude it, we designed a formal framework for building efficient incremental computations, and which supports custom state operators. And in future work, we want to investigate how to share the state to save memory of the incremental computation, and also ultimately we want to develop a standard library of differential operators for common data types. Okay, thank you for your attention.
Okay, in the back. Can I go ahead? You've got the mic.
Oh, okay, sure, thanks. Thank you for the talk. I was wondering, so it seems like most of your differential functions are user-defined. Have you explored synthesizing differential functions from the original definition?
We did think about it, but one interesting thing about the differential operators is these states actually are not intermediate results of the original computation. For example, the length of is empty is not sometimes not directly computed in original computation, so it's still far away from automatically synthesize efficient differential operators from our framework. Yeah, I think that's interesting.
Yeah, hi, back here. Lovely stuff. You mentioned that you implement all the relational stuff that existing IVM engines like differential data flow or DBSP do. How do you compare to them?
I think they apply in a more restrictive applications. For example, in the differential data flow, you require there is a partial order on the state, and also this actually poses some obstacles for using this differential application approach in a broad domain. So our method is actually more, in my opinion, it's more general.
That wasn't my question. My question was about how you compare on performance.
We did not compare the performance.
Okay. A sort of follow-up, I guess we can't look at the slide. We saw on that graph there were 3 lines. You only talked about 2 of them. One of them was the improved time performance, but it seemed like you were experiencing the exact same time-space trade-off that something like differential data flow or DBSP would have. Can you explain how you might achieve some of the sharing? You said that this was future work. Like differential data flow and DBSP can share arrangements. Yeah. What are you going to be able to share?
Yeah, for example, many differential operators use the input as the state. And suppose we connect 3 tail operators, list tail operators together. So obviously, they actually just use the same list, some part of the same list as their state. So for example, the first tail operator uses the tail of this list as the state, and the second tail operator will use the tail of the original input as state. So obviously, there are some opportunities for sharing the states.
Okay, thank you.
Yeah.
Okay, let's thank the speaker.
Okay, thank you.
Modularity, somehow using ghosts. Okay, thank you for your introduction. So this is joint work with my colleagues Matthias, Miriam, and Dominic. And I'm going to tell you how to extract modularity from interleaving-based proofs. So what does this actually mean? So first of all, consider this, this basic problem. You have a program and a specification, and now you want to know whether the program satisfies the specification. So you ask some automatic verifier, and it says, yes, it does satisfy the specification. So should you now trust this verifier? Well, probably no, because even if we prove the underlying verification technique to be correct, there still might be some implementation bugs. So even though the verifier says that a program is correct, it might actually not. So in order to increase the trust in the verifier, it additionally should output some kind of certificate. So a certificate, so it should not only say that a program is correct, but also give some reason for that. And such a certificate can then be automatically checked in order to increase trust in the verifier. And we want to work on concurrent programs. So we want to have certificates for concurrent programs, and they should be somehow compact, so they should not be too large. And additionally, it should be possible to check them efficiently, right? Such that you can just build a simple validator that does so quite fast. So how could such a proof for concurrent programs look like? So one approach would be something called interleaving-based proof. So here you can see a program consisting of 2 threads that run in parallel, so in red and blue. And what a verifier might just do to proving the program to be correct is just go over all the interleavings of the program, right? So here you have execute 2 actions of the first thread and then of the second and so on. And how could such a proof look like for this interleaving to be correct? Well, it could be just a sequence of Hort triples that, so that you start with phi 0, then you execute A1, then phi 1 holds, and so on and so on. And, right, but you have to do this for every interleaving in the program, right? So you pick another one, you get another proof, and so on and so on. And as an interleaving-based proof, we can then just consider a set of such formula that also is finite. So, however, the problem with that is validating such an interleaving-based proof cannot be efficient, right? There are exponentially many interleavings in the program, so we have to do exponentially many Hort triple checks, which is not good. So, on the other hand, there are thread modular proofs. So, as proposed by Obiki and Gries a long time ago, so the idea is there just to give invariance for each location of each thread, so independent of the other thread, and checking such a proof is relatively efficient, right? You just have to, of course, you need the usual inductivity checks, but in addition, you need also to check interference so that the other thread does preserve the invariant of the own thread. So, right, it might just assume that it's local invariant, but it has to show that the invariant of the other thread is preserved. And however, you still need to somehow reason about interleavings. So you cannot just give a completely thread modular invariance because it might not be possible. So for completeness, these thread modular proofs can also use ghost variables. So they can just encode some interleaving information, like for example, where the other thread is. Yes. And so here's a small example of a concurrent program. So you have two threads running in parallel, and we start with some state where x is greater than 0. And after both threads have terminated, x should be greater than 2. So in the two threads, they perform some operations on their local variable y and z, but in the end, they just increment x by 1. And the first thread additionally has some assertion that y should be less than x, but overall this program should be correct, right? Because x is initially 0, then each thread increments x by 1, so after that it should be greater than 2. Well, but how could a thread modular proof for this program look like? So first of all, we need some ghost variables because for example, at location L6, what is the value of x there? So it is either 0 if the other thread did not increment x, or it is 1 otherwise, right? So, and similarly for the other thread. So we need, but this is the only thing we need to track as interleaving information. So what can we do? We introduce two ghost variables, one for each thread. That's just Boolean ghost variables that just track whether the first thread has incremented x or whether the second thread has incremented x. And so consequently, we initialize both to false, and if x is incremented, they are set to true. So using that, we can then give a thread modular proof. So I will just show two invariants. So here, for example, at L6, before executing the increment of x, so of course the ghost variable is false. And as already said, if the second ghost variable is false, then x is greater than 0, so if the other thread has not incremented x yet, and otherwise it is 1, and at this point always y is also smaller or equal than x to check for the local assertion. And similarly for the other thread, right after it is incremented, so the ghost variable is true, and if the other thread is incremented, it's 2, otherwise it's 1. Okay. So now let's come to our contribution. So what are we actually doing? So as already said, we have some verifier that can produce an interleaving-based proof. However, they are not efficiently checkable. So instead, we want a thread modular proof, and our contribution is then just to convert an interleaving-based proof to a thread modular proof. Well, how do we do that? So first of all, we are working on so-called Petri programs, our approach. So it's just we represent the control flow of the program as a Petri net. So the initial place is represented with this marking, and we have the two error locations on the bottom. And right, if you recall the example, then it did not really matter regarding the proof whether what the second thread executed except for its increment. So it doesn't really matter if we are in the location P5 or P6. So, and what we do with such places, we group them into regions, so just sets of places. So here is one region with 2 places, and for the other thread, right, a region can also have just one single location, one single place. And such regions we can then group into territories. So it's just really an abstraction of the configuration of the program. And what we want to do then is assign each such a territory an invariant that holds there in order to construct a compact thread modular proof. And this leads us to empire. So here on the left you can see an example for an empire for this program. And what exactly is an empire? So, right, it's a finite state machine, so it consists of states, and of course also an initial state. And right, these states are connected with transitions over the program statements. However, additionally, we also have a territory mapping. So each state is assigned a territory, right, as already said, a set of regions that represent the configuration abstractly of the program. And additionally, each state is assigned a law in order to track the invariant that holds whenever we are in this state in the empire. The question is now just, how can we compute such an empire? So, right, again, here on the left you can see our Petri program again, and on the right there's an interleaving-based proof, right, just as already said before, just a set of formulas that are needed to prove every interleaving to be correct, right? We need to track whether x is greater to 0, greater than 1, or greater than 2, and additionally for the local assertion of the first thread, we need to track the relation of y and x. So, and how can we get an empire from this? So first of all, we start with the initial place, and initially true is the only invariant that we know. And then we simply execute an action of the program, right? There's just one outgoing edge, and the successor territory is then just P1 consisting of P1 and P5. And right, what invariant does hold there? So just x is greater than 0 since we executed it there. And now we continue like that. So we pick another transition here. X is not equal to 0. And what is the successor there, right? As already said before, it doesn't really matter regarding the proof whether we execute the statement or not. So, right, the invariant stays the same. And so the crucial part is here now, instead of just creating a new territory, which would make the proof really big, we simply extend it here, right? So, as already said before, it doesn't matter whether we are P5 or P6. It always, if the other thread is in P1, x is greater than 0. And so we continue like that. And right, similar here, the assignment of z doesn't matter for the proof. So, and the successor is already contained in the territory, so we just keep it. And then we continue like that. We pick a transition of the third thread again, right? And we still need to track the relation of y and x. So we just, we need to change the territory here regarding the first thread, right? Since the law changes, y has to be smaller equal than x. And then we continue like that. Here again, right, whether y is greater than 0 or not does not really matter regarding the proof. So we extend the territory and so on and so on. And if we do so for the whole program, we get the empire you've seen before. And right, it's already relatively compact. However, we actually want to get a thread modular proof on that. And how could such a thread modular proof look like? So first of all, we need ghost variables. And right, so the important interleaving information are just the states of this empire, right? And what we do, we simply introduce a single ghost variable that tracks the current state of the empire. And consequently, we initialize it to Q0 and we update it on every transition. However, we might omit updates if these statements just occur on loops. And right, and how could the invariance for each place then look like. So we can just have a disjunction. And what this means, right? For example, for P1, we see that it occurs in the territory of 2 of these states. And then we can just make a disjunction over these 2 states consisting of the ghost variable and the law. So, right, we have either the ghost variable is Q1 and x is greater than 0, or the ghost variable is Q3 and x is greater than 1. And if we do so, we get a Threadmüller proof can get a Threadmüller proof for the whole program. You see the invariance here in purple and the ghost updates in green. You see here the invariance for each of the places. And right, you see it's already relatively compact. There are at most 3 cases, so relatively good. However, what you may notice in the right-hand thread, there's still assertions or invariance over the variable y, which is just local to the first thread. It doesn't really matter to the second thread. However, we also developed a technique called focus that could get rid of these assertions. If we just, for example, if we prove the reachability of these 2 error locations separately, then we can make use of the modularity of the interleaving-based proof to get an even better Threadmüller proof. Okay. And we also evaluated our approach. So, right, as already said before, we use an interleaving-based proof to convert it to a Threadmüller proof. So we used the tool Ultimate Automizer as a verifier to compute such interleaving-based proofs. And to these proofs, we then applied our approach to get Threadmüller proofs, and we compared it to a naive approach as a baseline. So this naive approach simply encodes all the interleaving information, not only the one that's necessary. It just encodes the location, always the location of the other thread, which leads to quite a big proof, and it's inspired by the approach by Lampert, which was not really an approach, but just a proof that such Threadmüller proofs are complete. And as benchmarks, we simply used 1100 C programs from SV POPL'25. So, and what Automizer then did is translate these C programs to Petri programs, and then verified the Petri program. And if it did succeed, we got an interleaving-based proof, where then we could apply our approach. And the highlights of this evaluation is, right, compared to the naive approach, our approach was much faster, overall 119 times. And usually it just took 1 second or slightly more. And these proofs are also much smaller. So they are 15 times smaller than the naive approach, since we just encode the necessary interleaving information. And here's also a small graph that shows that. So in blue on top, you can see the size of the naive approach. And in red, there's the unfocused approach. And you see that there's a small improvement still if you use the focus as described before. And what was also a goal is these proofs should be fast to validate. So compared to the naive approach, they are 26 times faster. Okay, so then it's time to conclude my talk. So we presented an algorithm to transform interleaving-based proofs into Threadmüller proofs. And right, so therefore they can be used with different existing verification techniques. We don't propose just a new verification technique. And our evaluation has shown that the approach is feasible in practice. So the proofs are usually fast to generate and also to validate. And for future work, we plan to extend the focus. So we have already seen the focus to leave out some of the laws. However, we want to also extend this to ghost variables to omit also possible ghost upweights and thus even get smaller proofs. Okay, so then that's the end of my talk, and I'm happy to answer your questions now.
What questions do we have? So I'll start off with the future work. Are you hoping to express new proofs? Are there things that you'd like to prove that you can't currently do?
So the approach is complete. So whenever the program is correct, there exists a thread modular proof. And also, of course, the verifier needs to find an interleaving-based proofs, but it's just we want to get a smaller proof. And that could be then more easier to be validated.
Thank you for the nice talk. I'm wondering, so you're only focusing on this like concurrency, like the proving the concurrency in the program is correct. But what if I have a program that also have maybe some memory manipulation or some other features, and I also need to talk about this stuff. So is it compatible with your approach, or?
So you mean different specifications, or?
Yeah, suppose like you want to like verify some concurrent data structure, like some concurrent release or something like that, then you also need to talk about the shape at some point. And the question is like, how is it modular with respect to the shape part, or?
So well, we simply focused on these Petri programs, and thus relied on Automizer to get us a Petri program, so it can handle different specifications on the C level. And so in principle, our approach could be also applied to different specification on C programs.
Hello, okay. I guess you generate these empires automatically from the program. I wondered what the soundness condition is of an empire. For example, if you wanted to, for some reason, write your own empire and then check whether, is there a way to check whether it was sound?
Yes, sure. So, right, here's the empire. So you need to ensure that, basically everything here is inductive. So the laws have to be inductive, of course, but also the territories, right? So they have to respect the transition that is executed. And right, and of course also, right, we could also omit the error locations here, since they should have label false anyway. But if they are there, they should also be labeled with false. But you can give such an empire also manually. And we can then transform it to a thread modular proof.
Any final questions? Okay, well, let's go to lunch and thank the speaker.
Yeah, once the
I think you can send it, but yeah. Definitely don't press it on the cap.
Okay, so welcome to the monad and effect session of this afternoon. And we will be starting with one of the distinguished papers of the conference, an equational axiomatization of dynamic threads via algebraic effects. And Christina is going to give the talk.
Thank you. So this talk is going to be about denotational semantics for a form of concurrency where new threads can be created dynamically. And the main ingredients that we use to make this work is that we use abstract names to talk about ideas of pools of threads. And we also treat fork as an algebraic effect. And so the main point of this work is that we give a true concurrency semantics to a core functional programming language. But we also give a complete equational axiomatization for our semantics. And to do this, we use strong monads and algebraic theories. Okay, so the main idea of the semantics is that a concurrent program denotes a partial order with labels, also known as a POM set. Okay, here is an example program which it's probably hard to understand now, but the main point is that it forks a new thread, and then it performs some actions, row, sigma 1 and sigma 2. And its denotation is this POM set on the right, where the labels denote observable actions, and the partial order denotes dependencies between actions that we can observe. So here time is going from bottom to top. So that means that sigma 2 must happen before sigma 1. And then if two labels are not connected at all, that means they might happen concurrently. Okay, and then here are some more examples of POM sets that denote programs, and they are just to show you the kind of things that we can build. So we can also build a diamond shape or an N shape, and then this last one is a special kind of POM set with holes, which I'm going to explain later, which we need for our semantics. And of course, the POM sets are a very well-established model of true concurrency, but in our work, we go a step further because we also give a complete axiomatization to our POM set semantics, and we do this by using algebraic effects. Okay, so of course, there's a lot of related work on concurrency, which I can't put on a single slide. There's work in process algebra, in concurrent Kleene algebra. Other people have already used algebraic effects to model concurrency. There's been work on using separation logic to reason about effect handlers that implement concurrency, and we've seen some of that at POPL this year. But the key contribution of our work is that we give a true concurrency semantics to a functional programming language, and we do this through an equational axiomatization. Okay, so in the rest of the talk, first I'll explain what I mean by dynamic threads. Then I'll show you our algebraic theory, and then I'll describe the POM set semantics and the main theorem of the paper. Okay, so the language we're modeling has a base type of thread IDs, which actually they are IDs of threads, of pools of threads, because sometimes it's useful to refer to multiple threads at once. And then fork is the only operation that can introduce a new thread ID. And what fork does is it creates a new child thread and copies the parent continuation. And then, because fork returns some type, then a thread can check if they are in the left branch, then they are the parent and they have the thread ID of the child. And if they're in the right branch, then they are the child. And then waiting on an ID A means waiting on all the threads in A to finish. And then stop ends the current thread, and it signals to all the threads that are waiting on it that this thread is now finished. And then act just performs action sigma immediately. And these are the actions that we observe. Okay. So maybe you can see that this looks like a very idealized version of forking and waiting from POSIX, and this provided some inspiration. But what we are modeling is a fine-grained call-by-value lambda calculus with these 4 effectful operations. And the operational semantics is based on pools of threads. But I'm not going to show you the whole operational semantics, but I want to show you just some examples. And the main idea is that the observable behavior of a program is captured by a POM set labeled by actions. So in the first program, it starts by forking a new thread. And then there are 2 cases, one for the parent and one for the child. So the parent will do action sigma 1, and the child will do action sigma 2. And there is no dependency between these 2 actions. So in the POM set representation, sigma 1 and sigma 2 are not connected. But then, because sigma 1 is happening on the main thread, the parent, then it's connected to this special label S, which just signifies the main thread. Okay. But then, if I change the program a little bit, so I add a wait on A before sigma 1, that now means that sigma 2 has to happen before sigma 1, and this is reflected in the POM set. Okay. Right, and then I said that fork will copy the continuation of the parent. So this is what this example shows. So let's say that in the continuation of fork, there is an action row. And the point is that this action will get copied in the child. So in the POM set, we can see there are 2 row actions. And so this is the example from the first slide. Right, and then in this last example, I wanted to show that stopping actually ends a thread and throws away the continuation. So if there was an action row after a stop, then row will just disappear, and it doesn't appear in the POM set at all. And so what I will do later in the talk is axiomatize these 4 operations, fork, wait, stop, and act, using 9 equations. Okay, so now I get to the part about the algebraic theory. But right before that, I'll explain the type of thread IDs in more detail. So I said that it's a type of IDs of pools of threads. And so to refer to multiple threads at once, this type has a semilattice structure, meaning I can write terms like A plus B, and this refers to the union of the thread pools A and B. And then the term 0 refers to the empty thread pool. Okay, so in order to give the algebraic theory in a concise way, it's easier to use algebraic operations. But so far we have been using generic effects to represent the effects like fork and wait. So I want to first explain the correspondence between algebraic operations and generic effects before I get to the algebraic theory. So given a generic effect op that has type A to B, the corresponding algebraic operation will take a value of type A and one continuation for each possible value of type B. So we can apply this correspondence to the fork operation, for example, and then we would get this fork on the right that has two continuations, the parent X and the child Y. And the most important thing is that fork binds a new ID A, which is referring to the child Y. So A is bound in X. And because of this, fork is, well, it goes beyond the usual framework of algebraic operations, but it's still part of a well-behaved notion of theory, which I won't explain in this talk because I don't have time. So you can ask me afterwards if you want. And so we can apply this correspondence from generic effect to algebraic operations to all the other operations that I showed you. So wait will wait on all the threads in U to finish, and then it will continue as X. Stop has no continuation because its return type was empty. And act performs action sigma and then continues as X. Okay. And so the point is that these algebraic operations are just a different syntax with which I can write the same examples that you've already seen. And the POM set representation will remain the same. So yeah, you don't need to understand the details of how to translate from this top one to this one, but I guess the idea is that the term still starts with fork, and then there's one part for the parent and one part for the child. But with this new syntax, I can state the algebraic theory on one slide, which I think is quite nice. Roughly, the equations are divided into three groups. So the first one says that, well, the first one is about how weighting interacts with the semi-lattice structure on IDs. Okay, it's okay if you can't read all the details. And then the second group roughly says that waiting on A and stopping is a unit for forking, but it's a bit more subtle because we have to be careful about thread IDs. And then the last group says that waiting and forking commute with each other, and that fork is commutative and associative. And then the last equation about act just says that doing sigma and continuing as X is the same as doing sigma on a child thread while the parent is waiting for that thread to finish. Okay. So now I can explain the POM set semantics in more detail, and then also the completeness theorem. So the main result of the paper is this completeness theorem, which says that the terms in the algebraic theory of threads that I showed you just now correspond exactly to labeled partial orders with holes. And this is an extension of POM sets that we defined for our particular case, and that I'm going to explain next. And so this theorem also implies that the equations of the algebraic theory are both sound and complete with respect to equality of these POM sets with holes. And because we have this correspondence to POM sets, we can reason graphically about the terms of the algebraic theory. Okay, and this theorem doesn't yet say anything about how the semantics connects to the operational semantics, but I will get to that near the end of the talk. Okay. So far we have seen some POM sets that model terms. These are two examples that I already showed you, but these terms were all closed. So how could we model a term where there was a free variable like here, so like in this term where x is a free variable and also a is a free thread ID. So in order to model such terms, we introduced this extension of POM sets with holes. And the point is that the holes and the dotted lines that appear in these pictures, they are extra structure on top of a usual POM set. There is a way to interpret each of the operations as a POM set. So stopping is represented just as the empty POM set, sorry, not empty, POM set with one element that has this special label for stop. Then a variable is represented as a whole, labeled by x. And then this x has a potential dependency to the ID b, which is given by this dotted line. And the point is that x might use b in the future. And then because x is happening on the main thread, then it has a connection to this a stop label. Okay. Then waiting is also represented as a whole x, but now with an actual connection to the ID a, because x is waiting on a. Then act is performing action sigma before the whole x. And then forking has two holes, x and y, the parent and the child. And the parent has a potential dependency on the child y because it knows the thread ID of the child. And then again, the parent is the main thread, so it is connected to the stop label. And maybe the most important thing about these holes, x and y, is that we can substitute other POM sets into them. And that's when we start using the dotted lines. Okay. So now we can give the denotation of this term from the previous slide, which had a whole x. So yeah, that's represented as a whole here. Then x is waiting on a, so there is an actual dependency to the ID a. And x also knows about this ID b, which refers to row. So x has a potential dependency on the action row. Okay, and now that we have this graphical representation for terms, it becomes easier to understand what the equations in the algebraic theory mean. So here, I just copied the equation for associativity of fork. And in this graphical notation, it becomes easy to see that associativity just refers to different ways of plugging z into y and then y into x. So the two possible orders that we can do that in. Okay, I've already mentioned the completeness theorem, which said that equality in the algebraic theory agrees with equality of POM sets with holes. And because of this, POM sets with holes form a monad, which we then use to give a denotational semantics to language with forking, waiting, stopping, and act. And then we show that this denotational semantics matches the operational semantics from the first part of the talk, meaning that denotational equality implies contextual equivalence. And also we show that the converse is true, but only for programs of first order type. Okay, in summary, I showed you denotational semantics for concurrent programs that can fork new threads and wait on them. A key idea was to treat thread IDs very carefully. And the main theorems were the complete axiomatization of the POM sets with whole semantics, which we then extend to a mini functional programming language. And then show that this denotational semantics is both adequate and fully abstract at first order with respect to the operational semantics. And so in the future, there's many possible directions we could go in. And for example, we could improve the semantics to allow children to send values to their parent. And we would do this by modifying the types of stop and wait. We could combine our semantics with shared state, or we could explore alternative semantics for fork and wait, such as waiting on all the descendants of a thread to finish, for example. Yeah, and that's all. Thank you.
Thank you for the talk. Any questions? Yeah, maybe behind.
I was wondering about the expressivity of the source language.
Could you wait for the microphone?
Yeah.
Sorry, thanks for the talk. I was wondering about the expressivity of the source language with regard to the POM sets you showed in the first slide. There is the famous N POM set, and I was wondering whether that's something that's definable in your language.
The N POM set, yeah, it is definable. Yes.
How? Then I'm very curious to see how you do it.
Yeah, because, okay, I guess this is at the beginning. Okay, the idea would be that I can write a term where each action is a child thread. And then if I do that, if I spawn these threads in the right order, they can wait for each other.
Okay, so you can define any POM set then?
Yeah.
Okay, thanks.
I think it's working.
Really? Okay, yeah, okay. Okay, in the case of the state monad, which is much simpler, yes, the correspondence between the monad and the equational theory can be expressed as a normal form theorem.
Yes.
Yes. And so I was wondering whether the theorem, like the main theorem that you give,
yeah,
is expressed as a normal form theorem and some kind of rewriting theory, and how you do that, yes.
Yeah, that's exactly how we proved that theorem. Okay. Yes, by finding normal forms for the equational.
Okay. So it's purely
theory.
equational. Yeah, yeah. So
yes.
It's too good. I mean, it's really brilliant.
And
yes.
yeah.
Okay. Any more questions? Yeah. So maybe the next speaker could already set up.
I asked a technical question in the chat, but I have a simple beginner question. The associativity examples, intuitively we expect the three threads to be independent of each other, but the POM set you have in the middle looks like there is some sequential order.
Ah.
So what did I miss?
Okay, so right, so there, because X in that example knew the thread ID of Y, then there might be a dependency from X to Y once we substitute in another POM set for X, and that's what the dotted line was meant to represent. Yeah.
All right. So I think we should move on to the next talk. So thank you for speaking.
can sort of, yes,
Okay.
yes, yeah.
Good. So the second talk in this session will be given by Nick on handling higher order effectful operations with judgmental monadic laws.
Thanks very much. Yep, so this talk will be about, indeed, handling higher order effectful operations, and a little bit less about with judgmental monadic laws. But let's see where we get. So the story I want to tell starts with something that we should all know, which is we have programming languages, and they involve a relationship between software engineers and language designers, right? So your software engineers want to write some code, and that code gets executed or compiled by the compiler, and maybe you want the compiler to produce efficient code, or maybe code with like debug instructions or something like this in it, and the compiler takes care of all sorts of things like effects. But there are problems with this. So new effects can't really be added unless the compiler sort of supported them in the first place in some way. Existing effects can't be modified by the software engineer because they don't have access to the compiler. Maintenance is difficult. If the software engineers find a bug or something, they have to wait for the compiler writers to fix it. And compilation targets are fixed, so you can only have the 2 modes that were enabled by the compiler to start with. So we tried to fix this problem by adding effect handlers to the languages that we work with. So here's the same story, except we add one feature, that's support for handlers. And what that allows is for software engineers to modify various effects in their own right. And they can also add a whole bunch of effects that weren't conceived of in the first place. And it actually means that there are fewer features needed in the compiler as well. And finally, because they can define their own sort of semantics for code, they can produce new sort of output semantics. So for instance, they can decide to do some analysis on how much time it takes for functions to execute, for example, or whatever they might want. Okay, so that's kind of the motivation for what we're doing. And I'm not going to go through every single example here, but the point is that programming languages provide lots of different operations, and there are lots of different effects that might be executed. And so the real question is, can programmers add effects and control their implementations? And we think that effect handlers are a good way of doing that. They provide an interface for defining operations that are modular and composable. So I'm going to go through a kind of very concrete example of what this means. So suppose I just have a simple hello world type example here. It prints off, enter your name, then you type in your name and it says hello to you. Fine. So I can execute this. I type in my name, it says hello Nick, everything is fine. And suppose now I really wanted to encrypt anything that's been printed. So I can type this, and I just put an encryption under every single print that I have. And so eventually I can say hello encrypt. It's all been encrypted, it's backwards, and then I type in my name the normal way, and then of course it encrypts everything on the output. All right, fine. So now suppose I want to encrypt things, but I also want to time how long it takes for the user to input some data. So we have the standard print here, then we have a get time before and after we do the get line, and then we're going to type out the print but not encrypted, and then we'll encrypt the whole thing. Okay, so then we can execute this, and then it says, what is your name encrypted? I type it in, it gives me the time not encrypted, and then I can carry on with the encrypted output. Fine. So how could we maintain these different versions of this code for different purposes, right? So suppose that there were other things you had in mind. Maybe you want to do some debugging on this. Maybe you want to do it in production mode or with more testing information or with timing metrics, et cetera, et cetera. What would we do, right? If we're teaching this to first-year undergraduates in sort of good software engineering practices, they would say something like, well, maybe I just modify the code. Well, no, you shouldn't modify the working code. That's not a good way to work, right? You should keep the code that works as is, right? But maybe what you want to do then is you want to have copies of the code like we've got here with different versions, and you call out to the one that you want. But the tricky thing now is if there's a bug in the original piece of code, then you've got n different versions to maintain, and that's not good either. So maintenance is also a problem, so you don't want to do that. And so the thing that we turn to is algebraic effects. We say, okay, maybe what we can do instead is reinterpret the way the operations work themselves. That way we can keep the original code as is, and we can yet change the meaning of that code when it's executed. So here's that same code on the left-hand side, and on the right-hand side, I'm going to just show you what you can do with effects. So it's the same piece of code. We still have the hello. The only thing that's changed is the type signature, where I'm actually saying this code involves printing and getting. And what I can have instead is this thing called a handler. And this handler says it's going to intercept any prints and produce prints. So here it is intercepting any print message, and it's going to add an encryption to it instead. And here's a different handler, which intercepts any get lines and replaces those with stuff that involves time, does get line, and also prints. So when it sees a get line in your code, it's going to say, I'm going to get the time, then I'm going to do the actual get line, then I'm going to get the time and print out the time that it took to do something. And what this allows now is for us to be able to compose handlers together to give a new semantics to the kinds of things that we're doing. So for example, here's the encrypted time handler, which first encrypts the words that we have, then does the timing stuff, and then produces some I/O action. So if we were to execute that, we would get the version where the printed stuff has been encrypted, but the time hasn't been encrypted because that's not gone through the encryption handler at this point. But of course, and the good thing here is that we've managed to modify our behavior of the hello program without modifying the hello program itself, right? We've changed the way that the operations have been interpreted, and we're happy because we've gone beyond the first year where we've had to change our code in bad ways. But what we can also do now is we can we might be able to commute our handlers down here. And by changing the order of these handlers, what we're saying is we're going to get some timing information, and then that's going to output some strings, and all of that's going to be encrypted, along with everything else that's been printed too. So if we do the timed encrypted handler on the same hello program, then you get the encrypted prompts, you get the unencrypted get line because that's when you're typing things manually. And then, of course, the time has been encrypted now, as well as the final messages. So what's nice about this is that we've been able to easily add additional behaviors simply by changing the handlers that are dealing with things. So far, so good. This is the standard effects and handlers story. But now there's something that is a little bit perplexing. So suppose we have a program that looks like this. It's a program that does some stuff, and then at some point says, handle the hello program with a timed encrypt. I suppose we've got a different program that does basically the same, but uses the different handler instead. So this time it's doing encrypted timed. The question becomes, what if I wanted to choose between these two different programs, and I want to be able to do that by modifying the way that we're going to handle things, right? And this is almost the same question that we had just a minute ago, except that I'm now asking myself, how do I change what handlers are being chosen, rather than how do I change what the operations are doing? And we want to do this in a way that's suitable. So we've gone through the reasons why this is bad for ordinary operations. It's also going to be bad for handlers. So we can't just modify the handlers and say, well, I've changed my mind and delete all the code and replace it with something else. And so again, we want to say, well, can we perhaps somehow reinterpret the handlers themselves in different contexts? So can we have handlers? That would be nice. So perhaps along the way, we decide what we're going to do instead is have a sort of sensor operation. So here we have some kind of censoring with an encryption scheme. And then we might have two handlers that deal with that censoring and does it in an uncensored or a censored version. But the trouble is that censor itself is not a first order thing. It takes as one of its parameters this hello program, and which we can sort of see here as this parameter here. And unfortunately, that just means it's not an algebraic operation. It doesn't fit what the framework is expecting. It's what we call a high order effect, and that's the kind of thing that we deal with in our framework. So that's kind of the motivation for this, and I'm going to go into the more sort of theoretical construction around how we get there. So we're using a kind of CBPV type semantics where we've got pure values. So here the turnstile has no sigma annotation. That means it's a pure value. And so we can construct things like values, we can construct things like operations, and we can sequence things using let bindings in this way. And typically what we do in this domain is we talk about algebraic operations, which are just a shorthand for saying that we have a let binding followed by some kind of computation. Okay, and there are lots of operations that we can handle in this way. Again, I won't go through those in too much detail, but the point is that you have some kind of fixed parameter and some kind of arity, and you can pass all these through, and it all just works as you'd expect. So the key point with effect handlers is that what we want is the handlers to sort of reinstall themselves automatically into the continuation. At least that's the perspective for deep handlers. So we can see that in the rule for how we do operations. So with a particular operation, what we're going to do when we handle with some h, big H, is we execute the kind of interpretation of that operation, which is sensitive to the parameter v and k that's going on here, so sensitive to the parameter and the continuation. And what we're going to do is just substitute the actual parameters into the formal ones. But in particular, in the continuation parameter, we reinstall the handler big H on the residual program Q that we're going to carry on with, right? And this is quite key. It's what we would call a deep handler, because it's automatically taking care of the bureaucracy of reinstalling handlers for you. And I think that's really critical, because it means that when you're writing algebras for these things, or when you're writing the semantics for these things in these little h's, you don't have to think about what's going to happen with the recursive call. The framework is taking care of that for you. That's really critical here. And then, of course, this framework allows you to give different versions of handlers. And so here's the kind of more theoretical way of saying exactly the same thing that I said earlier on. We have different handlers. That's great. But if we want to have catch, we can sort of imagine it being a handler like this. But in a program that has multiple nested catches like this one, we might ask ourselves the question of, well, how about if I want to reinterpret catch as retry or some other semantics instead, which is the problem that I was showing you in the concrete earlier. And we know we don't want to modify the program P so that we replace catches with retries. We know we don't want to redefine catch as retry. That would be just modifying the source code of that. What we need instead is the idea of making catch an operation and then handle that somehow. So one way of doing that, and I think it's the one that most experts ask me first, like, why don't you just do this, is what I call the quick and dirty approach, right? What you do is you have the catch operation, and as its parameter, you put in code. You say, well, there's nothing wrong with code being a parameter. We can just pretend it's just a ground type like everything else. Maybe it complicates the denotational semantics somewhat, but somebody clever can sort that out for us. That's fine. But that's what people do in practice, and so you can imagine you've got your program P, your program H, and we're going to handle these. And the way that we might deal with this is we could create this new handler called retry, which observes the catch operation, which now has programs as its parameter, and does something like this. Now, I don't really care too much about what this is actually doing. What I want to point out is that in the handling clause A, big H here, we are reinstalling various handlers into the subcomputations. So under catch, we have our program and our handler. We need to execute P and handle it with this big H, and we also need to execute H and handle that with big H. And the point I want to make here is that this really undermines the fact that we're using deep handlers in the first place, because now for these kinds of operations, where the payload, the parameters contain programs themselves, you, the handler writer, have to think about reinstalling things yourself. And I think just 2 minutes ago I said, isn't it a good thing that in deep handlers we don't have to do that? Well, here we're doing it all over again. So the big point is that we want to avoid this explicit reinstallation, and we want that to be taken care of by the machinery itself. And that's where we get onto doing scoped operations in a slightly different way. So we can basically redesign our language so that we have native support for these things called scoped operations. And they essentially look very similar to before. They still have this idea of parameter and arity, but they're going to be examples where we have, as one of our parameters, or as the continuation, is going to tell us how many programs are going to be needed to spawn off to deal with whatever interesting effects that we might have. So for example, catch, so there's one operation catch that takes in one parameter, and it has arity 2, which means it has 2 programs that you might be interested in once you're dealing with this operation. So the first one being the ordinary program, and the second one being the program that handles the effects of that one. Or here's another one with the same signature, which is parallel operation. So there's one parallel operation, and it wants to do P1 and P2 in parallel, and so it takes in these 2 arguments. With is another example. So with says, with some resource R, that R might be something like a file or a network socket or something like that. We want to have one program that comes out, and that program is going to be somehow sensitive to that resource that's in play. Another example is maybe like some control structures, like if or while loops. So an if takes in some Boolean, and then it produces 2 programs, or at least 2 programs might be sensitive to that Boolean. So this might be if you want to, I don't know, have a lazy version of if then else, or maybe an eager version that executes both branches, or who knows what. Maybe you're doing some kind of like static analysis of your code. You want to reinterpret how if works, and similarly with while. So the only real difference so far between these and scoped operations syntactically is that we're just indicating that they're scoped with these curly braces rather than the round braces. That's all that's going on. And so at this point, I think it's good to just reflect a little bit about on the different sort of presentations of operations that we've got. So we have the generic operation that we started with. And what I sort of briefly noted was that we have a kind of rewrite rule that just says, actually, generic operations are just the same as algebraic operations, which have this round parentheses around to say where the continuation is. And that's subject to this law that says that you can always sort of you can commute the let into the parameter. One way of reading this particular law is to say that this parameter is kind of irrelevant, right? It's that you can always just bind freely. And so in a sense, that's why generic operations don't need this in the first place. So long as you have let bindings, you're fine. But the reason that it's often stated this way is because we enjoy writing the handler operating semantics with that continuation K explicitly marked so that your particular algebras can deal with that continuation result and do something with it. So in a sense, the reason that this is useful is for the description of handlers, although in terms of syntax, this might be a more sensible way of doing it. The scoped operation is different, right? The scoped operation has this parameter here, which denotes the sort of continuation of programs that you want to handle before you continue after this operation. And I think some of you will validly say, hang on a minute, you're just playing tricks here. This is exactly the same as the algebraic operation. All you've done is changed the brackets, right? That's not a sensible distinction to be making. My point is that actually this is not a law, right? We don't have the algebraicity condition, which means it's relevant whether or not we have the operation by itself or whether we have it under a let binding. Those are two distinct things, and they shouldn't be confused. So that means that when we try to handle such scoped operations, so here's the scoped operation, we need to be a bit more careful with what we're doing. And ultimately, you can see that we have this handler H, which deals with the continuation explicitly here. There's something to do with polymorphism going on here, which deals with the fact that you could have nested scopes, and you don't quite know how nested you are. You need to deal with those differently. But the point that's important is that when you're faced with something like this construct here, where you have let A equals op vj in Q, you really can't translate that into just a simple scoped operation as you did with the algebraic version. You can't just do away with the lets and absorb that into the continuation parameter. What you need to do instead is explicitly handle the operation with the J jump parameter, let's say, and interpret Q separately, and then somehow combine these two in some sensible way, preferably doing this thing first before this thing on the right. Okay, so we need to combine these two computations, and if you look at their types, you can see this has type MA, and this type has type MB given some A. Well, that reminds us of something if we're familiar at all with monads. But that's not where the literature went. So the literature went slightly different. Bosman, Vandenberg, Tang, and Shrivers wrote a paper about this problem where they do the same thing that you would do in the algebraic effects setting. That is to say, you extend your scoped operation with an additional continuation, just like you did with the generic operations for algebraic. And then you give a semantics where the handling algebra H takes into account the continuation that comes off of that and continues from that way, right? And so in this way, the thing to note is that your algebra is sensitive then to the continuation on the outside of this. And so we have kind of like you can imagine this being called like the algebraic scoped version or something like this, I don't know, right? But there was a different solution, which is the one that we take in this paper. And the solution is to say, actually, maybe we should be handling let. We keep operations just as they were, we keep val just as it was, but we now explicitly have a way of dealing with let. So that means that we're going to have handlers that need to take into account this M parameter, which basically has to handle the context for a let. So it has some P, which is a program, Q, which is a continuation of this, and then brings you back to this point. Now, if you look at this, you get really suspicious because now you really are looking at bind. If we just compare the two, I just want to sort of emphasize that both of them achieve roughly the same thing, right? But the difference between them is a bit like the difference of the universal property of lists. There are two universal properties of lists. There's lists as the initial fixed point of the particular functor where you've got a value constant onto some stuff. And you've also got the universal property of lists as a monoid where you keep hold of that monoid structure. And we're seeing these two different versions here where in this second one, we're kind of remembering the fact that we're interpreting into a monad. And so we're allowed to kind of use bind in our semantic domain. What that means is that when we write equations in the style of number 2, we're allowed to talk about bind. We're allowed to talk about what happens with the monad itself, which means we can talk about interactions with bind and other operations, which we couldn't do in the first version. So the deep scoped handler looks something like this, where essentially we're going to say we want to be able to take care of the let op version of things. And the idea is basically that we reinstall the handler under each of the jump parameters here, where we reinterpret all of those. And then once we've finished interpreting all of the jumps, we then bind onto the interpretation of Q prime. But this bind here, so this is sort of syntactic sugar for the M that comes out of interpreting this thing. So you can just imagine that this operation, which is sensitive to P and Q and X, can be turned into a bind operation. And if you know that you're interpreting into a monad, that really is the bind that you want to play with. So I think that's basically the main message of the paper. It's that when we're handling scoped things, we have a choice, and it's sensible to work in the understanding that you're going to be interpreting things into a monad. That allows you to have a richer language for equations afterwards where you can incorporate that in your understanding of what's going on. So the paper itself takes a very different exposition to what I've given you here, right? So in the paper, we do the presentation of the theory not with the traditional gamma and turnstile presentation, but rather we go quite categorical, and we work with a logical framework instead. And our computational semantics are proven using realizability models instead, which prove consistency of the model and give us the executional semantics of that as well, so that we can actually have assemblies that tell you that you can execute our programs. So that's how we deal with sort of the operational side of things. And then rather than working with traditional logical relations, we work with synthetic tape computability and then do our proofs that way. So I see that I've got about 3 minutes left to talk. So I was going to call this the end of talk, but maybe it's not really the end of the talk. To give you just kind of a quick flash through some of the constructions of doing system F omega in a logical framework, we'd get something that looks like this. So the logical framework is basically a Martinov type theory, which contains judgments J and various widgets that you would expect. And I just wanted to sort of have a side-by-side comparison for you for what things look like in the paper. So on the left-hand side is the traditional gamma and turnstile presentation that you'd be used to, and on the right-hand side is the exact translation that we'd have in the paper. So here's the rules for kinding. Here are the rules for kinding application and abstraction on the left-hand side, which are all usurped by this single rule on the right-hand side. It's just witnessing an isomorphism. And this is the kind of compact stuff that we really enjoy in that paper. Of course, that's achieved by just expanding some definitions, but that's kind of the purpose of this. And again, on the right-hand side, we're doing some interesting logical framework stuff. And the kind of key contribution of the paper itself is actually not just this, it's actually working towards system F omega ha, which is F omega extended handlers. This is basically where we add in a CBPV style thunks, where we've got forcing and thunking. We can talk about things like the laws of computations as you'd expect. And then the handle construct that I gave you earlier on is slightly generalized so that we're dealing with higher order signatures instead. So the rule that we give in the paper is this, but that translates to something like this in the turnstile way. And what's interesting is that the proof basically is about whether or not we can have well-behaved enough programs such that this works out. So as I said, this paper is supposed to be not just an investigation of, let's say, higher order operations and how we can handle them. I think that the message of the paper is that we should be really thinking about bind itself when we're giving semantics to things which involve sequential computation. That's not news, but it seems to be news when we're thinking about algebraic operations. The second thing is it's really a tutorial in, well, maybe tutorial is too strong a word. It's an example of how you might do semantics in a way that doesn't involve the traditional gamma and turnstile. Thanks very much.
All right, thank you. So I think we have time for maybe one quick question.
Just a quick question about the dynamics. You know, how you started designing this work? Were you more on the turnstile side or more on the categorical?
This was designed more from the categorical framework perspective.
Since the beginning, and
yeah.
and what it brought you, and why it was in the end a natural option.
Yeah, that's right.
I think it's a good question.
Yeah, it's a broad question. So I think the goal was really what happens when you kind of stubbornly stay down the categorical route right the way down, and then you come up with some nice semantics, and then the rest is
kind of guideline. I mean, for the guide.
Yes,
towards,
exactly. It was the guiding principle.
As it should. Yeah. Okay.
Yeah.
Right. So thanks, Nick, again.
Thanks.
If you could put that on your call.
You're all set?
Yeah.
Okay. So, so we move on to the third talk in the session, which will be given by Wen Hao on growth and capabilities as modal effects.
Thanks for the introduction. So I'm going to talk about how to encode different effect systems into modal effects. This is joint work with Sam Lindsay. So what are effects? They are the way that the programs interact with the environment. And many examples. Effect types, also called effect systems, statically track the use of effects in types. And there are many different kinds of effect systems. Perhaps one of the two of the most popular ones are either based on role types, as in the language Coca, or capabilities, as in the language effect. So in Coca, every function type from A to B is annotated with an effect role E, which represents the effects that might be used when the function is applied. And in effect, functions are called blocks, which are second class, using this double arrow. And it not only binds a list of normal arguments of type A, but also a list of capabilities F of type T. So a blocking effect can call these capabilities F bound here, and may also call some other capabilities provided by the context. So as we can see here, their function types look quite different, and it is not obvious how to encode between them. And I think the main challenge is that their effect tracking mechanisms are deeply entangled with function types. This is reminiscent of the classical situation of encoding between callback value and callback name, because when two sunk and or false computations is entangled with functions in callback value and callback name. The great work on callback push value subsumes both by decoupling sunken and falsing from functions. So why don't we do this for effect tracking? Why don't we decouple effect tracking from functions? This is what our previous work did. So we have this Uppsala paper on modal effect types, which decouple effect tracking from function types using modalities. And this paper shows that how such a system can significantly reduce the verbosity of effect polymorphism in traditional systems. And in this work, we do something different. We propose a uniform framework to encode and compare different effect systems based on the idea of modal effect types. So these are what our encodings look like. So for function types in Coca and effect, we encode them as function types in math with some actual modalities written as these square brackets or angle brackets to explicitly simulate how effect tracking works in different systems. And in the remaining of this talk, I'll try to explain what it does. So what are modal effect types? The key idea is to have a notion of ambient effect context, which are the effects provided by the context. So here is the typing judgment of a first order function. It takes an integer x, calls the yield operation, returns a unit. This add syntax tells us that the current effect context is yield, so we can call the yield operation. Here is another example of a higher order function. It takes a function argument f of type int to unit, an integer x, applies f to x, add the ambient effect context yield. So effect context is propagated through types and terms. So for this higher order function, both the argument function and the result function are at the ambient effect context yield. And there is a natural notion of sub-effecting. So say that we have a function that only calls yield, we can of course type check it at a natural context with both yield and ask operation. Keep in mind that effect contexts are part of typing judgments. They are not part of types. And whenever we want to check effects in types, we use modalities. We have absolute modality written as a square bracket with some effects E. It changes the ambient effect context to E. So here is a function whose ambient effect context is only ask, and we use the mode syntax to introduce the absolute modality of yield, which changes the ambient effect context from ask to yield. So for the premise, its effect context is yield. It also introduces a knock in the context, which I'll explain later. And we also have relative modalities written as angle brackets E. It extends the ambient effect context with some new effects. So here we have a function which uses both the yield and ask operations, but the ambient effect context has only ask. We use this mode syntax to introduce the relative modality of yield. So for the premise, for the inner function, its effect context contains both ask and yield. And it also introduces a knock into the context. These knocks control the accessibility of variables. So here is an example of an invalid judgment. It is unsafe because we have a function argument in the context whose effect context is ask. It may use the ask operation, but we want to call it instead the absolute modality of yield, where only the yield operation is present. Mat rejects its expected premise by not allowing the function argument f to be used after the knock of the absolute modality of yield. So these knocks control which variables can be used and which variables cannot. In order to make it well-typed, we can annotate the variable binding of f with the empty absolute modality, which tells us that f is actually not at the ambient effect context of yield, but at the empty context. So it is a pure function. We can use it wherever we want. And such a binding is introduced by modality elimination. Supposing we have a value v, which is a function from int to unit, with the empty absolute modality, we can use the net mode syntax to eliminate the modality. So we have a binding f, a function from int to unit, with the annotation of the empty absolute modality. So these are the main ideas of model effect types. If you get lost, don't worry, because now we are moving to encodings. So first we'll encode rows as model effects. So we consider the calculus system F epsilon, which formalizes the Kokas row-based effect system. The idea, as I have mentioned, is to annotate each function arrow with a row of effects E, which represent which effects might be used in this function. I'll give some examples of system F epsilon. So this is a first order function, takes integer x, calls the yield operation with the argument x. So it has a function type from int to unit, annotated with yield, which is the operation that is used inside this function. And here is a higher order polymorphic function. It's the standard application function, but abstracts over an effect variable epsilon. So the argument function f might use the might use effects epsilon, and the result function may also use the effects epsilon because the result function calls the argument f in the function body. For the middle error, it's pure. Its effect annotation is empty because the middle function does not call f directly. So our encodings for system epsilon is very simple. It encodes an effect for function type in system f epsilon as a function type in MET with an extra absolute modality with the same effect. So for the first order function, we encoded it as a function type from a unit to unit with the absolute modality of yield to reflect that it is a function that may use and may only use the yield operation. For the encoding of the term, we just use the mode syntax to introduce this modality. For the second example of the higher order function, it is similar. So the higher order function has 3 function arrows. We introduce 3 absolute modalities, one for each function arrow. For the argument function and for the result function, they both use the absolute modality of epsilon because both these functions can use effects in epsilon. And for the middle arrow, we use this empty absolute modality because it is the pure function. And the encodings preserve polymorphism. So for the quantifier of the effect variable epsilon, we just preserve it in the encoding weight. Yes, and for the term, it is still very similar. Module knows this mode and net mode syntax, which explicitly introduce and add limited modalities. So as we can see here, our encodings kind of use modalities to explicitly simulate what effect tracking does in system f epsilon. Okay, now we encode capabilities as the modal effects. We consider the calculus system C. It is the core calculus of effect. As I have mentioned, the idea is to treat effects as capabilities provided by the context. So a block, which is a second class function, binds a list of arguments of type A and a list of capabilities F of type T, and returns some value of type B. So I'll give some examples. The first one is, again, a first order block. It calls the capability yield provided by the context. So in system C, we use these curly braces to create a block. It takes an integer x and applies the capability yield to x. Its type is just int to unit, because system C allows blocks to use arbitrary capabilities from the context without mentioning them in the type. And here is a higher order block. It not only binds a value variable x, but also a capability variable f from int to unit and applies f to x. So the binding of the capability f not only appears in terms, but also in types. So it is kind of similar to some form of dependent types where we have bindings where we have term level bindings in types, and may mention it later. So blocks are second class, they cannot escape. So if we look at the example of this application block, we can call the capability f in the block body, but we cannot return it because returning f would allow f to escape its lexical scope. So in order to write a current version of this block, we need to use boxes. So for this new higher order block, it binds the capability f and it returns another block from x to f of x. And we box it in order to make a second class block into a first class value. So the type of this return value is int to unit at f is a block from int to unit, and the at f syntax tells us that this block uses the capability f. So as we can see from this signature, types in system C can bind some variables and can mention these variables later. Our encodings of system C look like this. It is very involved because a block construction in system C does several different things. So first, for this example first, it binds a capability variable f. This variable f both appear in terms and in types. The block body may call this capability f, and the block body is also allowed to call some arbitrary capabilities from the context. Our encodings make these different things explicit. So for the first one, we introduce a type level variable f star and wrap the argument with the absolute modality of f star. So by having a type variable here, we are able to mention the term variable f at the type level. So it is similar to singleton types, if you know what singleton types are. And by wrapping the argument with the absolute modality of f star, we make sure that whenever we call this argument, f star must be present in the context. And for 2 and 3, we use the relative modality of f star to wrap the whole function. So first, we use a relative modality which extends the ambient effect context with f star, so we allow this block body to call f star. And second, because it is a relative modality, other effects provided by the context can still be used. For encodings for boxes in system C, we encode them as absolute modalities. So for the current version of the application block, the return type int to unit at f is encoded as a function type from int to unit with the absolute modality of f star. So which tells us that this return function may use the capability f. So let's wrap up. Now we have seen some examples of encodings of system f epsilon and system C into math. By observing these encodings, by only observing the encodings of these types, we can have some interesting observations. So first, different top-level modalities are used in the encoding of different types. For system f epsilon, every function type is encoded as a function type with an absolute modality. Well, for system C, function types are encoded as a function type with a relative modality. And we only use an absolute modality in system C if we have a box type. So it tells us that in system f epsilon, function types always fully specify which effects might be used. While in system C, block types never fully specify which capabilities might be used. You can use arbitrary capabilities from the context without mentioning them in types. And we only fully specify the capabilities they use when we box them. The second observation is that effect variables are inserted at different positions. In system f epsilon, the encodings use effect variables only if the source type uses effect variables. But for system C, whenever we encode a function type, we introduce a list of effect variables. So it tells us that capability variables in system C perform some role, are kind of like some explicit form of effect polymorphism. And it explains why, like, if you look at some code neighbors of effect, you'll never find explicit effect variables because capabilities can do complete rules of effect variables. we have more things in the paper. We have the full formalization of the uniform framework, which we call MAT-X. And X is an effect structure, so it is a parameterized variable following some previous work, which allows us to abstract over different treatment of effect collections, which are orthogonal to how they track effects. And we have some extensions to make our framework more expressive to include more other systems, and some standard meta theory of type summoners effect safety. And we have encodings of various different systems, including 2 core calculi of COCA and 2 core calculi of effect. So I have only shown encodings of function types in the talk, but we also encoded effect handlers. And we proved these encodings preserve types and semantics. And yeah, I think that's all of my talk. My takeaway is we should decouple effect tracking from function types, and by doing so, we can have a uniform expressive framework which subsumes existing effect systems. Thank you.
All right, thank you. Any questions? Yeah.
A beginner question. In the COCA translation, I would expect the E absolute modality to be on B, and not on the whole function type. Why is it on the whole function type?
Why it is on? You expect it to be assigned B.
I would have guessed A arrow E B.
Right. So a modality overrides. So a modality overrides the whole effect context. So by having an absolute modality here, we are seeing that for the function from A to B, its effect context becomes E. And this effect context E propagates through type structures. So it is a function that might invoke effect E. But if we mode this absolute modality inside this function, then it means something different.
I have another question if you don't have. So I expect that it's possible to make a monadic translation for the COCA effect system. So you start with the effect system and you go into monads in a system with no explicit effect system, but monads to represent the effects. And I was wondering whether we could factor the monadic translation through your translation. So maybe the usual monadic translation, if it exists, could be defined after your translation.
Sorry, I didn't quite answer the question.
No. I think there's a bit of a misunderstanding there. There's not really a fundamental difference between the presentation of effect type systems where you write the E on the arrow versus the Wadler style where you write T of E applied to B. There's something quite different going on here. The modal effects are contextualizing all of the effects. So you don't gain anything by trying to do the thing that you're suggesting. That's not actually doing the decoupling that we're going for. But we can talk more about that offline if you like.
I have a quick question. So I might be misremembering, but I have notes from your Uppsala talk. I have written down here that you originally designed the MET system to try and subsume effect polymorphism, so you explicitly didn't want this as a feature of the type system, and then you of course added it here to correctly model this thing. So was it originally there? Like, did you expect that you needed it?
Yes. So if we want to fully simulate traditional effect systems, we do need effect polymorphism in MET. But our Uppsala paper shows that, so in our Uppsala paper, we identified a large fragment of traditional effect system and encoded it into MET without effect variables. So it is not the full system, but a subset of traditional effect system. Yes.
a quick question. I mean, it was very impressive and also enigmatic. So I was wondering whether you have in mind at some point to look for some kind of semantics, like monads, and what you do is so much beyond. I mean, and looks like extraordinary. It would be interesting to have a mathematical description of what you mean. Yes. I mean, typically this polymorphism and effects, and you graph the whole map, the whole arrow, and how you could try to describe that using tools of, let's say, semantics, categorical semantics. So. I mean, okay. I mean, in a way, the success of monads is that they are beautiful for programming and also they are beautiful mathematical models. Mm-hmm. So I'm just wondering whether you have that in mind. That's it.
I don't, but I do want to. I don't for now, but like the whole calculus is based on some quite theoretical work on multimodal type theory, which does have a categorical semantics, and I expect we could generalize their categorical semantics for this work. So yeah, I think there's some future work to be done here.
All right, so I think we should move on. So thanks for now again. Maybe could move on because I want to put my microphone somewhere. Okay. Great. So it's my pleasure to announce the last talk of the conference, which is relative monads and their meta language. And Zev is going to give the talk.
Hi, everyone. I'll be talking about the relative monadic meta language. This is joint work with Jack Lealcock and Sam Staton. So back in the 90s, I was in a very famous TV show, and Eugenio Moggi introduced the notion of a computation type, which has gone on to quite transform the past 30 years of functional programming and allows us to understand effects in a typed way. And in particular, he also gave us terms for given a value, returning a sort of trivial computation that just returns that value, and for sequencing computations. But it's a bit odd, something that's a little odd about the monadic meta-language, which he introduced, is that even though it doesn't have function types, it's inherently a higher order language because you can iterate T. So the type TTA, which is the type which has of computations which would return computations, well, if you think about what it is in, for example, standard ML, where the monad is just unit to A, it's very explicitly higher order, but it's also has higher order aspects in other settings. And it's not really used for sequencing computations. Also, mathematically, it's often very strange and very difficult to manipulate. So sometimes, I'm not saying that higher order things are bad, right? We've seen a lot of nice higher order effects in this session, but it's nice to separate out the first order aspect from the higher order aspects and study the effect in a first order setting and add in function types and higher order aspects later. So we provide essentially a first order language based on relative monads, which now separates types into two different sorts. So there's ground types, which are types which you can do computations on, and effect types, which are types for modeling computations. So now they're separated into two sorts of kinds of things. And this means you can't iterate T in particular. And we provide a sound and complete semantic. The reason this is called a relative monadic meta-language is we provide a sound and complete semantics using a new notion of strong relative monads. So there relative monads are now quite old and have been very well studied in a variety of categorical settings. And there have been suggested definitions of strong relative monads already. but they don't capture the computational aspects of strong relative monads. So we provide a new definition which subsumes previous definitions and also gives a computational interpretation. So something that's quite interesting about this separation into two sorts is you now have two options if you want to program in an effectful way, right? So previously there was only one sort. We only had one option. You had to program directly with the computation types. And you can still do that. You can still have your programs living in these effect types so that computation types are sort of first-class types that you are writing programs between. And we'll see an example of this in this talk. But what's interesting is we can now do our programming in the ground types and just have access to this extra space of effect types which we can model computations in and then pull things back. And this means you can model computations in very interesting ways, as we'll see as well in this later in this talk. So this isn't just a philosophical talk. We have some actual applications in mind. So monads have, over the last 30 years, been taken in all sorts of directions. So they've been generalized, specialized. So for example, arrows are a generalization of monads. I'm going to work right to left. Arrows which model like non-sequential effectful programs. Graded monads model resource usage sensitive effects. So something where you keep track of costs or effect usage. And finitary monads or enriched algebraic presentations of monads give you ways of directly handling a particular effect with extra terms and can be very useful when actually programming with monads. And these can all be unified as particular instances of relative monads, and so can be put in our framework and give very interesting languages for these and many other generalizations of monads. So what is the relative monadic metalanguage? Well, as I said, we separate things out into ground types, which are types that computations can be done on, and effect types, which are types that model computations. We have contexts, which are lists of effect types. And this is pretty important because we want to be able to store computation variables in the context for more expressivity. And we have standard terms for returning a value on a ground type. So J, we have two types of ways of turning ground types into effect types. J just interprets a ground type as an effect type, and T provides computations on the ground type. So given a value of the interpretation of a ground type as an effect type, you can return a computation, which is the do-nothing computation, and we can sequence computations on ground types. And these have to satisfy some equations that mean that sequencing is associative and unital. So as a concrete example, let's turn to programs with randomness. So these are programs that take in some input and with some probability come out without some other output, and often are modeled semantically via stochastic matrices. So rows are non-negative and sum to 1. But these have been known to been modeled monadically via functions from a finite set to distributions on another finite set. So you have this set D of M, whose elements are some weighted distribution, where for each thing you get a non-negative number and they sum to 1. And these are equivalent perspectives. But this finiteness is actually pretty important when it comes to probabilistic programming. So, for example, in the language DICE, which is a finite probabilistic programming language, the inference algorithm requires the space to be a finite type. And if you wanted to have a typed finite probabilistic programming language, this D of n is not finite anymore. It's a different sort of type for programming. You have to treat them differently, especially when it comes to these inference algorithms. Furthermore, while it's possible to define an iterated D, it's not really a useful mathematical object. So there are distributions on distributions that are studied in probability and statistics. The famous Dirichlet distribution is one such. But this doesn't appear in the set. I mean, you have to turn into more continuous or measurable settings to find these, and they have their own problems for semantics. So we want to model the actual restriction to finiteness, so we do probability in the relative monadic metalanguage. So now the ground types are going to be finite sets, and we add in an additional term called coin, which represents a fair coin flip, which returns true with half probability and false with half probability. And then in this language, we can start to write equations, right? So the first equation says that if you flip a coin and you do nothing with the result, that's the same as just the result in the first place. The second equation says if you flip 2 coins, then it doesn't matter which order you use the results of these 2 coins. And the last equation says that the coin is actually fair, so if you flip a coin, then you can use the true or the false as your output. So these are famous equations. They're known as Stone's equations for barycentric algebras, and they can be written in the relative monadic metalanguage. And these equations, alongside the monad equations, so associativity and a unitality of sequencing, provides a complete axiomatization of this model of finite stochastic matrices if you restrict to dyadic rationals, but you could obviously make it all stochastic matrices if you added in coins of every bias. But this provides a nice, simple example. And this example is not limited to probability. I showed you probability because it's clear that you need this finiteness understanding, but there's many, many other algebraic presentations that can be done within the relative monadic metalanguage. And we give another example of local state in our paper. And in fact, many of the languages that people have been using in the past were instances of relative monadic metalanguages. Okay, so this gave you an example of the first setting where we're doing the programming in the effect types. Later we'll see an example of an example where we're doing the programming in the ground types. So what's semantically going on? Well, distributions is a functor which takes in a finite set and returns distributions on that finite set. So it goes from finite sets to set, because the distributions might be infinite. The interpretation of ground types as effect types is also a functor. It just says a finite set is also a set. But this distributions functor has additional structure for being able to return values on ground types and sequence computations on ground type. And this is known as the structure of a relative monad. So given more generally an interpretation of ground types as effect types and computations on ground types and a way of returning values on ground types and sequencing computations on ground types, this is the definition of a relative monad. So just to make it really clear, I'll put a monad and a relative monad next to each other because many of you are probably more familiar with a monad. So the key differences are a relative monad is a functor from ground types to effect types. It's no longer an endofunctor. It can only return values of a ground type, and it can sequence computations on ground types. And in fact, it should be clear by this comparison that a monad is actually just a relative monad. Sorry for using the word just. When you you set the interpretation to be the identity functor. But actually, it's not enough to just have relative monads because we need context for our programs. We need to write programs with variables, right? And often multiple variables. As you saw in the equation I showed you before with this commuting 2 coins, we needed 2 variables. We needed multiple things in the context. And in programming languages, the way that we have monads with context of variables is using the notion of a strong monad, which allows you to thread context into sequencing effectful programs. So here you have a program which returns a effectful type A, and another program which depends on A but produces something effectful of type B. But it could have other things in the context, right? And we need to provide something from that context effectful of type B. So we need to have a way of sequencing in context, which is this contextual bind operation. So how do we do that for strong relative monads? Exactly the same. We provide a contextual bind operation for sequencing computations on ground types in a context of effect types, because the context may have computation types in them. Otherwise, and then it satisfies some equations, like a strong monad does. So with this new notion of strong relative monad, we can provide a completeness and soundness theorem that says that our language presented before can be interpreted in any Cartesian category with a strong relative monad on it, and also the term category of our calculus. The term model of our calculus is one such example of this. So now to look at the other side of the coin, pun intended, in terms of modeling in the relative monadic metalanguage, we're going to look at an example where all the programming is happening in the ground types, but we have access to these ambient types living in the effect types for a particular type of modeling computations. In this case, we're going to look at graded monads. These are well-known semantic tool for modeling effect usage sensitive computation. So think about cost. That's the analogy I always have in mind. So now for each A, we have a computations of cost M type, TMA. And the relevant terms are also cost sensitive. So if I have a value, the computation that just returns that value, it doesn't do anything, right? So it shouldn't cost anything to do that. And so it's of type identity cost computations on A. But if I have an M cost computation and an N cost computation, and I sequence them, I run the M cost computation, I feed it into the N cost computation, the resulting computation should be of cost M plus N. So this is graded by a monoidal category in order to capture this addition and unit costs. One thing to note here is that M is an explicit parameter, external parameter of our language. However, not in the wrong slide, sorry. There's an example of list, which is a very famous example of a graded monad, which is graded by number of choices. So list models non-determinism. At each point, I can branch in many ways. And a natural way of thinking about costs of branching is how many branches do I have to investigate, right? Like, do I if I branch 2, then that's a lot more work than branching just one. So here we have a function which outputs 2 things, and then we have a function that outputs 3 things. And you can see that the composite can output at most 6 things, and so is graded by naturals with multiplication. We can model graded monads in the relative monadic metalanguage by adding explicit grade types first class into the language and model them linearly. So now we have ground types, which is just the simply typed lambda calculus, right? So it has products and exponents. And we have effect types, which is the linear lambda calculus. It's going to be modeled linearly because grades track resources, so should be modeled linearly. And then we add in a linear-nonlinear adjunction. So we have a way of turning effect types back into ground types and producing effect types from ground types. And all we do on top of Benton's linear-nonlinear calculus is add on a relative monad. So with this relative monad and first-class grade types, we can model graded monads. And the fact that they're first class is really important for multiple reasons. You recall that in the previous version it was an external parameter of the language. So firstly, they're modeled in the calculus as linear, so they actually do respect the resource sensitivity that we want them to. Secondly, it's much more flexible in terms of implementation, right? So we don't have to put in all the grades. We can just construct grades within our language. And it has a lot of reusable code. So the bind, for example, is written exactly the same for all the grades, and so it's one step towards sort of grade polymorphism. So once we have this set up, this relative monadic metalanguage, which has linear effect types, we can write a graded monad on the ground types as such, and And then we start to see the real advantages of having a linear part and a nonlinear part to this language. So having nonlinear ground types allows you to program as normal if you wanted to write any sort of graded effectful program that you want. So say you have a program from A to A, which is effectful of cost m, right? You want to be able to sequence this with itself, right? That relies on nonlinearity because it relies on duplicating it, and the duplicating term should cost m plus m because you sequence it with yourself. So here I've written a sort of nonlinear function which duplicates f and sequences it with itself. But the linearity of the E-types is also really important for enforcing this cost of computation. So here we have a program that will run a computation of cost m on A and run a cost of computation of cost m on B and return both outputs. That should cost m plus m, but if this E-type was modeled non-linearly, we could feed in the m variable twice into the computation, and then the resulting computation would only cost m. So it is actually a very important condition. So we have now two languages for graded monads. How do they relate? Well, this language for graded monads with just explicit, everything is externally imposed in order to provide a language for graded monads, embeds into our calculus because we have a graded monad on ours, and this is a conservative embedding, so we can't prove any more equalities between terms in our language than in the traditional language for graded monads, which everything is externally imposed. How do we prove this? Well, it's quite tricky, but first step is you take a graded monadic metalanguage model, that's a Cartesian category with a strong graded monad on it, and you take presheaves on it. And presheaves is now going to be a Cartesian closed category with all limits and co-limits. And so you can show that this is part of a linear nonlinear model, which consists of, in this case, E hat valued, but here I wrote E because they're different E, maybe I should have made that clearer. So if you have a Cartesian closed category with all limits and co-limits, then this provides a linear nonlinear model. And we saw before that when you have a linear nonlinear model and a strong relative monad on it, you obtain a graded monad, but that was one way. In this case, because there's loads of limits and co-limits and this is a particular model, you get away the other way around. So if you have a graded monad, you can construct a relative monad. So this shows that every graded monadic metalanguage model embeds into a model for our calculus, and it embeds fully faithfully, and that proves conservativity. So if there's one slogan that I want you to take away from this talk, it's that relative monads allow you to control computation, right, in two different ways. And we saw both sides of the coin in this talk. So first, you could do your programs in the effect types, and then ground types control where computations take place. So for example, if you want to have a typed finite probabilistic programming language, you can put finiteness guarantees on the thing that you're running computations on. But you could also have your programs living in the ground types, and then effect types control how computations are modeled. So we saw one example here where the effect types are modeled linearly, and then we can have a linear usage of effects, and so model graded monads. But what are the full contributions of our paper? Well, we provided a framework metalanguage with complete semantics via a new notion of strong relative monads. We provided a first-order syntax for enriched algebraic theories in this setting. And we provided a new language for both graded monads and for arrows via our framework, and proved conservative extension theorems for both of them, which extend the previous known calculi for graded monads and arrows. Thank you. That's
beautiful, I think. So any questions?
What about relative graded monads?
Yeah, that would be quite interesting. I don't know if it would fit into this particular language, but it's definitely something that would be interesting to see whether you could extend it in that way. I mean, something that we did note is that having this relative monadic framework for example, graded monads, gives you a better semantic understanding of how to extend things, so how to add in additional language features. It seems easier in our framework.
And are graded relative monads different than relative graded monads? Okay. You don't have to answer that.
Right. Any more questions? Yeah.
Hi, great talk, really interesting work, and I'm trying to stitch together what the parts are on here. So you introduced, you pulled in linear and non-linear and this kind of adjoint model because you wanted to have things treated linearly, but that adjoint model of two categories and that connection between them is, in fact, that kind of doesn't really have to relate to linearity at all and is collected to kind of call by push value and other constructions. So I mean, is in fact your relative monad construction an instance of this adjoint calculus in the first place?
Thanks. Yeah, so there's a lot of interesting connections to call by push value. Certainly, in the sort of primitive framework model, there's no way to get back into the ground types, and so you do need to add an adjunction if you want to do your programming entirely in the ground types. And as you say, a linear non-linear model is in particular a call by push value model, and so the question is whether this can be viewed as built on top of call by push value in some way. There is another work which, ordinarily you can't necessarily force computations here, which it makes it slightly weaker than call by push value. There is another work that Max Nu and others have looked at where you add a relative monad on top of call by push value, which looks like, well, it doesn't have strength, which is a little different from how we approach things. So there they rely on the sort of unary stat context to work with ordinary relative monads, at least as far as I understand that work. But there's definitely interesting connections that we would like to.
Okay. So I mean, in some sense, yes, what you have things are. In some ways, these are weaker than other models of these things because you can't. You want to have this separation. You can't necessarily get forced computation.
Yeah.
Something's very.
Yeah.
But it seems to be moving towards something in a kind of a la carte thing of you want this combination of features, then what you have is a relative model or something that's called by push value or linear non-linear, and they're all shades of similar structures, but you just need to be explicit about which of these features, which are clearly delineated, do you want in your system.
Yeah, I think so. I think semantically, a relative monad looks very different to a sort of a call by push value model, but they can be sort of melded together in interesting ways, I think.
Right, thank you.
Time for one more question, maybe? Yeah.
Whoa. You showed this example where you defined you had this R of M lolly. Maybe if it's possible to go back to that. Yeah, this graded monad. That looks a lot like a graded adjunction. Is this something you've thought about, maybe in line with the previous question?
In the sense that this is a sort of graded reader monad, or?
Well, I'm just thinking maybe you have, I think as far as I understand, a graded adjunction consists of a J and maybe an R and a T, at least in some formulations, and maybe this looks kind of like call by push value, where R is the right adjoint and T is the left graded adjoint. Have you thought about something like this?
I mean, this is, in particular, a sort of like built on a call by push value kind of thing. But there is, the relative monad is playing a very important part in the definition of this. So this relative monad built on top of it is pretty critical.
All right, so I think we should take further questions for the coffee break. So thanks, Seth, and everyone.
Okay, so welcome to the Types 3 session, which we're about to start. So our first speaker today is Celia Lee, who will be speaking about a complementary approach to incorrectness typing. Thanks, Celia.
It's not playing. The slides are not playing.
Slides aren't working.
Mm-hmm. So first we start with some motivations. We want type systems that can certify both that some programs cannot go wrong, that is, there's no runtime errors, and we also want it to be able to say that some program cannot go right. However, traditional typing is about proving correctness, so if it type checks, we know it definitely cannot go wrong, but if a checker rejects a program, we usually don't know, does it really go wrong? Like in this very short expression, we are trying to do arithmetic on a non-integer, or the program actually lies beyond the reasoning power of the type system. So that program does not exist in that type system, even it will evaluate successfully. And therefore, we want some reasoning system that can offer sound incorrectness proof that if the program is ill-typed, then it must go wrong. Then we need to find some way to describe what does going wrong mean. So different typing language, for the purpose of different safety properties, there might be different kinds of going wrong. Like for the first example, we simply have a classical type safety error. Because the beta rule does not apply to the term anymore because it requires a lambda abstraction. And we might have pattern matching errors because we don't have a branch that can actually go to, and we are just stuck there. Or we may even have memory safety errors. For example, if we already after free something and we try to use it again, the operational semantics that is requiring that is requiring that the location we are trying to read all right. So since we already free it, the heap now is already empty. So we do not have the load rule does not apply to it anymore because that location is not in the domain. And in the end, we have an example of successful evaluation. So even this this program has a problematic branch. We never reached that branch, so it actually still evaluates successfully. And we are making an observation that a program goes wrong if it reaches a bad state. That is, it's not a value, but there's no further reduction step can make. And now we can formally define what means going wrong. That is, a program goes wrong if it's reduced to a stuck term. And as we have seen in the previous examples, this definition is capable to derive going wrong with respect to different safety properties. And now we have seen that a program's, so all normal forms can be partitioned into values and stuck terms. And these are actually dual endpoints where evaluation stops. So this suggests that we should be able to reasoning about correctness and incorrectness in a uniform way. And a type system can be a formal system for reasoning about how terms will reduce to normal forms rather than just reduce to values. And so how what how would we interpret type as normal forms? We are working in a universe of all normal forms. And we have some values, and for value types, this interpretation does not make any difference. But at the same time, we also have stuck terms that previously does not exist in the scope we consider, and it's natural to consider type that corresponds to the universe of all normal forms, and we can if we also have a type OK that classify all values, and since it's a partition, if we have some sort of complement operator, we can then describe the type that classify all stuck terms, and that type operator can be applied on any types. So if it's on int, then then that type would contain both non-int values and stuck terms. So this set theoretic models of type semantics suggest some useful tools that we can use for reasoning, and we already suggest that we already suppose we have an complement operator, and this complement operator is essential because we cannot avoid to be able to describe some negated shape constraints. For example, we may need to describe something that is not an integer, and and that is the root cause of the program go wrong. So our type needs to have some yes, it's some way to describe that so that we can reasoning about it. And sorry, I'm not sure I'm using the correct slide. Sorry, this one is correct. All right, so the set theoretic interpretation immediately gives us two reasoning tools. First is the complement type operator, and then it's the subtyping relation calculus, and we can treat the subtyping relation calculus as some meta theory of complement type operator. And both are sound with regarding to the model, and the subtyping relation define the correct, the desired behavior of complement operator by the interplay between them. It can define some, at the base type level, we can define the disjointedness, like the integer type is disjoint from an atom type, and then we can have one is the subtype of the complement of the other. And we also have the normal order reversion evolution. And using those rules of subtyping relation, we can reasoning properties about complement type operator. And we are just going to have some quick intuition check, like that for function types, we have one function type is another function type subtype if it satisfies these conditions. It's natural if you think about the set of normal form these two function types denotes, and therefore, we can conveniently have some abbreviations that we have a bottom type, which is the complement of the top type, and then the bottom to top type already denote the set of all lambda abstractions. And the other, or actually the most important reasoning tool, which is complement. This is important because refutation principles needs to be able to express negative shape constraints. for example, if we are trying to applying a non-function, then the app-e rule say that wrong application would lead to MA has type OKC. And if we're trying to do arithmetic on non-integers, by the way, this is a multi-succedent system, so this rule means if one of the argument is not integer, then we will get an error. And even for pattern matching, we need some way to say that it is not possible that match any pattern. P are patterns, and for any value that substitute to that pattern, it's impossible that M has that type, and therefore that match expression must stack. And because we're working on the normal forms, complement would behave logically like a negation. So refuting M has type A would be equivalent with verification of the complement typing. So the complement actually offer a bridge between the proof of correctness and incorrectness. And the preservation and progress gives us give us the soundness that as long as we can prove M has type OK, then it cannot go wrong. Because any term must either diverges or evaluated. And once it's already in a normal form, the progress suggests that it must be a value. And similarly, if we can prove M has type OKC, then it cannot evaluate successfully. So for the verification rules, they're just normal rules we are familiar. And well, maybe except for the match rule. Here, the match rule, we put the M on the left because this work is actually mainly done in a two-sided setting. And we will soon see that with complement, we can we can derive typing rules of two-sided system from the normal one-sided system rules. And we also have refutation rules. So for the two-sided typing judgment, it just leaves the restriction on the left context. So now we don't require the left contexts are all variable typing. They can be terms, and these semantics intuitively should be very similar with the normal judgments. For example, for the power function, to have a type of integer, we must, it must be that the input y is an integer. However, it's not true that x must be an integer because this term always, by definition, evaluates to 1 if the second argument is 0. So because we now allow terms typing on the left as well, and because complement behavior like a logical negation, we therefore can derive some left roots or refuting roots from the one-sided system. So here, this necessity arrow is defined as A complement to B complement. It means if for the function to output an B, it must have received an A as input, and by the two complement rules, we can derive the left up L rule for refutation from the right rule. That if we know this function only output an A when it receives an B, I forgot to mention another thing, that is for two-sided type system, we actually we can read the judgment as the typing on the left are refutation, because if we imagine the right context is empty, then the informing reading would say that if all formulas in gamma hold, then then at least one formula in delta holds. But since there's no formulas in delta, when the right-hand side is empty, it must be that the left typings are some refutation. And here, these gamma are just arbitrary, delta are just arbitrary side contexts. So we can read it as, we know the argument is not a B, and we know the function must need a B to output an A. So we reject that the application has a type of A. So this kind of two-sided rules can be derived from every one-sided typing rule, and we can view them as a kind of sequent style term typing, although it's not on the type connection. But so it's not right rules and left rules for type connection, but right rules and left rules for the type constructor. So here, the left is in left rule for the constructor of application, and the right is in right rule of the constructor of complication. Since our system is trying to do constructive proof and refutation at the same time, we realize that there's a kind of well-studied logic that do similar things, which is called bi-intuitionistic logic. So this is a kind of logic that has a combining power of both intuitionistic logic and co-intuitionistic logic, while intuitionistic logic is for constructive proof and co-intuitionistic logic is for constructive refutation. And usually the bi-intuitionistic logic reasoning system is often presented as some sequent calculus style rules, and we realize that it is also the case for our two-sided system, that it looks like kind of some sequent style of term typing, and therefore we are considering about the necessity type for function refutation. We first realized that it does not compose well. Oh yes. So we can have the coverage function for the arrow type that we have two we have two arguments at the same time. So I forgot to put the coverage rules on the slides, but inspired by the co-arrow in the co-arrow in the bi-intuitionistic logic, we define a co-arrow type as the dual counterpart as the arrow type, and with this definition, we can derive left rules that have lambda terms coverage just like the normal arrow type, like they would at the right.
Sorry, we're going to have to...
Oh, yes. Oh, yeah. So these are the two most messages I want to express. One is type should... we can interpret a type as a set of normal forms, so that through complement we can have a formal reasoning system for both correctness and incorrectness, and the complement yields a co-arrow which can be viewed as the type counterpart as the co-arrow in the co-intuitionistic logic that can compose this when we are refuting okay.
I think, could the next speaker start to get ready? And if we have one question while they're getting ready, that would be great.
Have you considered implementing the type system to play with it? Do you have an implementation?
No.
Okay, well, thank you very much. So our next speaker will talk about multiple types. Thanks.
Okay. Yeah, thanks for the introduction. This is joint work with David Castro Perez and Francisco Ferreira from the University of Kent and Royal Holloway. I'll proceed in two parts with this talk. In the first part, I'll cover the second half of the title, namely the existing work on multi-party session types. And then in the second part, I will cover the first half, namely our contribution in this area. But before I get into any of the technicalities, let me first say a few things about the general context in which the work took place. So, in general, I think the long-term research goal here is to make concurrent programming easier. And the kinds of concurrent programs that we are looking at in this particular paper are those where we have a bunch of processes that communicate with each other using channel-based message passing. Okay? And for this class of programs, we want to help programmers reason about safety and liveness properties, and in particular those that pertain to the message passing behavior that the processes engage in. Okay? And the way that we do that is by providing programmers advanced type systems that can take some of the burden for these programmers. This is, in very broad strokes, what the paper is about. Now, let me be a bit more precise about which problem in particular we want to help programmers with. So, imagine that we are programmers, and after doing a lot of work, we have written both a specification and an implementation of our concurrent program. And I'll assume that our specification consists of at least 3 pieces of information. First, we need to know something about the processes that this program consists of. We also need to know something about the channels between those processes. And finally, we need to know something about the expected message passing behavior that the processes engage in. Or in other words, the communication protocols they need to comply with. Now, given these 3 pieces of information, one of the complicated challenges that we now need to address is somehow prove, or at least convince ourselves, that this implementation is safe and live relative to the specification, where safety means, informally, that bad communications never happen, while liveness means that good communications eventually happen until the program possibly terminates. Okay? Now, over the past 50 years, I think many techniques have been developed to help programmers with this, and as I mentioned before, we are looking at type systems. Okay, so the idea behind these type systems is that they will be sound in the sense that if each of the processes is individually well typed at compile time, then we want to conclude that the parallel composition of those processes is safe and live at runtime, right? That is the goal. Now, in general, this is called behavioral typing, and one particular flavor of behavioral typing is multi-party session typing, and that is what we look at in this paper. So, let me try to explain how this works on one slide. Our starting point is that we have this implementation and the specification, and in this very simple example, our implementation could look something like this, right? So we'll have 4 processes, which we'll implement in terms of 4 terms in some kind of programming language. Now, because this example is so simple, our language, in this case, needs to have only 2 primitives, namely sends and receives. Sends are represented by the exclamation mark, receives are represented by the question mark, right? So Alice starts by sending value 5 to Bob, and Bob correspondingly starts by receiving a value from Alice stored in variable x, which is supposed to be of type not, so it's a number. Okay? I'm also using this square bracket notation, which is just syntactic sugar for multicast, essentially, but the details don't matter so much. Okay? So we'll have terms that implement the protocol. Now, we also need to have a type that specifies the protocol. And again, because this example is so simple, I can write the type using only one kind of type constructor, and it looks something like this. Okay? We have this arrow here, which means, A arrow B means, a message is communicated from Alice to Bob, right? And the type of the message should be a number. Okay, that's our only type constructor. And then on the right-hand side of the semicolon, we have another type that specifies the continuation of the protocol. Right, this is the idea. This is our starting point. Now, if we want to do multi-party session typing, we now need to proceed with 2 steps. In the first step, we'll extract from this total specification at the top a partial specification for each of the processes that defines exactly what that process is supposed to do to comply with our protocol. So for instance, for Alice, we have this partial specification that says that she needs to send a number to Bob, and for Bob, we have something that says that he needs to receive a number from Alice, right? There is this duality here, Okay? Now, normally in the session types literature, we call these total and partial specifications the global type and the local type. And the process of extracting the local types from the global type is called projection. Okay, fine. When we have projected this global type onto each of the processes, so we have all our local types now, then the only thing that remains is to type check each of the processes against its own local type. And this is essentially by sort of syntactically matching the structure of the type against the term. Right? If they somehow correspond syntactically in this way, then we can conclude well-typedness. Now, in this very simple example, we have only 4 of those terms, but in general, we can have any number of processes. Right? So then the picture looks like this. We start from a global type, do our projection to obtain the local types, and then type check the processes. Now, suppose that we go through all of these movements. What really does that give us? Let me be more precise about what time soundness formally means. And I'll do that in terms of these classical notions of progress and preservation. So the progress theorem could be formulated something like this. Assume that we have some predicate phi on collections of local types. And it doesn't really matter at this point in the talk what exactly phi is, but it is apparently something that we need. So, okay, fine, we have it. We'll also assume for progress that we have the parallel composition of the processes, represented with this capital pi operator here, that is not yet terminated. Okay, so down arrow here is the termination predicate, but they're not yet terminated. And we'll also assume that each of the processes is individually well-typed. Then we can conclude that there exists a bunch of next processes such that the current processes can make a transition to the next one, right? So they really can make progress. Now, similarly, we have preservation, for which we apparently also need to have this phi property. But now we assume that we already know that the processes can make a transition, and they are still well-typed. And then we can conclude that there exists a bunch of next local types, such that each next process P prime is typable by this next local type, right? So typability is really preserved by these transitions. Now, the interesting thing here is that these next local types, they don't sort of appear out of thin air. There turns out to be a very nice, interesting relation between the next local types and the current local types that we start with, which is typically represented through a transition relation. Okay, so we take somehow a kind of operational view on these local types. We interpret them basically as automata or as state machines. And then we have this transition relation defined for our local types that we can use to synthesize these next local types from the current ones that we already have. Okay? Okay, so progress and preservation, this is what we all can prove, and then we combine them, and then we have type soundness. Okay. Now, in principle, this is all fine, but the practical applicability of these theorems crucially relies on our ability to establish this phi property. And for a long time in the community, we sort of assumed, or we thought, that we get this property essentially for free. We thought that if we start from a global type, do our projection, then this phi property is sort of entailed through this whole process, or by this whole process. So we have it by construction. Now, unfortunately, a few years ago, in POPL 2019, Skalas and Yoshida show this is, in general, not really the case. Right? So for the simplest of multi-party session type systems, yes, we have it, but if you make it a little bit more complicated, a little bit more expressive, then you lose this satisfaction of this assumption. And so I guess I'd like to emphasize that the theorems, they are still true, but they're applicable just far less often than we originally intended them to be, so to speak. And so this is somehow the current state that we are in. We have this original approach from 2008, which is basically what I've been talking about so far. And then 7 years ago, we have this observation by Skalas and Yoshida that say, yeah, okay, but this phi property is not really entailed by projection. And so what they do in their paper, they also propose an alternative approach that sort of fixes this situation. And I will call this approach the less is more approach, because the title of this paper is Less is More. So colloquially in the community, when you talk about the less is more paper, then it's generally understood that it's about this paper. Okay, fine. So the idea behind this less is more approach is that given this observation that projection does not entail phi, yeah, why would we do projection at all? Right? Can't we just skip this whole layer of global types and projection and do everything just completely in terms of the local types? And that is what Skalas and Yoshida propose. So they have these local types, they have a separate proof method to establish this phi property for families of local types, and then they formulate the whole meta-theory around this thing purely in terms of those things, without global types. This has been a very influential paper in the community. So over the past 5 years, I think many people have adopted this approach. It really is, right now, I think, the state of the art. So what we add to the state of the art in this paper is essentially another solution to the same problem. So we still need to deal with the fact that phi is not entailed by projection, but instead of saying we get rid of the global types and do everything in terms of local types, we explore the idea of keeping the global types and removing this intermediate layer of local types. Okay? If you do that, we still don't need projection anymore, and as it will turn out, we also don't need this phi property. So that is essentially what we want to do in this paper. Now, why would you want to do this? What is the advantage? Well, it turns out that by doing so, we can somehow recover the compositional nature of this whole type checking approach that was part of the original paper, but that was somehow lost in this less is more approach. Because in this less is more approach, in addition to just type checking your processes, you also need to do separately a kind of global analysis, right, on the state space of your local types, which is sort of non-compositional in nature. Okay? And so with this approach that we propose in this paper, we do have a kind of compositionality. So to summarize the contributions, we have a new multi-party session type system where we type check processes directly against global types instead of projection and local types. And then we show that by doing so, we attain the same level of expressiveness as the less is more approach by Scalas and Yoshida. So what they have in their paper, they have kind of a benchmark set of example protocols of which they show that they're the first ones that they can actually support them. And we show in our paper that we can support the same protocols, but in a compositional fashion. That would be the novelty in this respect. Okay, so that's one thing. Then we zoom out a little bit, squint our eyes, and then it turns out that there is a kind of a nice generalization of this type system where instead of using global types, we look only at the transition relation of the global types, or in other words, labeled transition systems. And so what we do is we formulate the whole meta theory purely in terms of those labeled transition systems, LTSs, and then separately we show that this general case, in a formal sense, really subsumes the special case. So if you were to use global types, then yes, you also enjoy the type soundness result that we prove primarily for well-behaved labeled transition systems. Okay, now these are all the, let's say, theoretical contributions of the paper. All of this is supported by an artifact in which we have a formalization of all the results in Agda. So all our proofs are machine checked. And we also have a proof of concept implementation of the special case. So we have a Visual Studio Code extension with an LSP server that runs a parser and a type checker, and then you can sort of, in a toy implementation language, you can write types and terms, and you get syntax highlighting and red squigglies if you make type errors. So that's very nice to experiment with the theory, I suppose. Okay, now what I want to do in the rest of the talk is just try to convey the main intuitions behind the techniques that we use. Okay? So the goal here is to have a type system, multi-party session type system, where we use, or where we type process terms directly against global types. That's what we want to do. And it turns out we need to proceed in 4 steps. The last step that we do is proof progress and preservation, which are now formulated like this. It's essentially the same as what I showed you before, except that we now have global types as our types, and we no longer need this phi property. Okay? Now, if you look at the formulation of these properties as progress and preservation, then we can identify 3 things that we need to define before we can start doing any of the proofs yet, namely the operational semantics of the terms, the operational semantics of the types, and the typing rules that link everything together. Okay? And so in the paper itself, we have lots of these kind of inference rules. I don't want to show all of them today, but I just want to show you the simplest ones for the simplest features of the language, just to convey the general idea, right? That is the idea. So let's start with the operational semantics of the terms. I'll show it here only for individual sends, individual receives, and communications. Those are the most interesting ones, perhaps. So for instance, on the top right, we have an output process, right? And what this rule says is that the output process can make a transition to the next process P prime if we can evaluate E, which is the message that we're sending, to a value V. And then the label on the transition is a representation of the send action that's being performed. So PQ represents here the channel from P to Q, and V is then the value that we're sending. Now, similarly, we have such a rule for receives. And for communication, right, if we have an output process and an input process, and we put them in parallel, then we basically just synchronize their transitions. That's what's happening here. Now, I should emphasize, these rules is a completely standard. This is just concurrency theory. Our contribution is not on this part, but I mean, we need it, so I needed to mention it here. Similarly, we have an operational semantics for the types, which in its simplest form looks like this. So we had this type constructor for a single communication with a continuation G prime. Well, again, we can make a transition to G prime. And the label in this case represents the whole, or specifies the whole communication that is allowed, so to speak, by this type. What you should notice now is that let's say, the structure of this transition label for the type is the same as the structure of this transition label for the parallel composition of the terms. And this is important because in this way we can sort of link the behavior allowed by the type to the behavior actually realized by the terms, right? So this is important if we want to formalize safety, okay? Now, finally, we also need to have some typing rules, and they look something like this. So on the bottom left, the typing rule for output processes says that this output process is typable by G if from G we can synthesize a next global type G prime such that at least the next process P prime is typable by G prime, right? So we have this inductive application of the typing relation. But also, of course, we need to know that the send action itself complies with the communication that the global type prescribes, right? So we need to have that the receiver Q is the same and that this message E that you are sending is of the right type T. Okay? And if this is all the case, then we can conclude that this output process is well typed by G. Now we have a similar rule for receives, and then if we want to type the parallel composition of an output process and an input process, we just type those processes individually, and then we can immediately conclude the typability of the parallel composition, right? So this is the compositionality that we were actually looking for. Now in the paper we have lots of additional features in our language. So we also have branching and selection, both at the type level and at the term level. We have recursion, right? So you can have cyclic transition structures as well. We have if and let. So ultimately, this program calculus is Turing complete. And we have something called skipping. Now, skipping is quite an interesting phenomenon. It's the idea that if I am Carol, right, and I need to be typable by some type G, but this G has only a single transition labeled with a communication from Alice to Bob, right? Being Carol, I am not involved in this communication. So for me to be typable by G, basically, I should just skip this transition and show my typability against G prime. That is the idea of skip. Now, in this very simple example with only one transition, this is easy. But if you have arbitrary branching in your transition structure and recursion or cycles as well, then it gets a lot more complicated. And so the most difficult typing rule for us to get right was actually the one that supports this kind of skipping. For people who've seen multi-party session types before, this is very much related to merging in the classical approaches. Okay, we do all these 4 steps, and yeah, then we can write the paper, submit to POPL', and then we are happy. That is sort of, in a nutshell, what happened here. Okay, there's one last thing that I want to discuss. I am now, I would say, finally in a position to sort of highlight what I believe is the most interesting novelty, technical novelty of this work, which is that the typing rules of our system are what is sometimes called synthetic. And synthetic in this context means that in our typing rules, we have meta variables that appear in the premise of the rule, but not in the conclusion. So to give you an example, this was the typing rule for output processes, right? We type it with G. Then from G, we synthesize G prime, and then we use G prime to type P prime, but G prime itself does not occur in the conclusion. And this is very different from most of the typing rules in the existing multi-party session types literature, which are what is sometimes called analytic. Analytic in this context then means that each meta variable in the premise also occurs in the conclusion. And in particular, if you look at this, let's say, representative rule for output processes in the traditional multi-party session type sense, then we still see that P prime needs to be typable by, well, in this case, local type L prime, but that's not really the point. It still needs to be typable by L prime, but this L prime, it syntactically already occurs in the conclusion of the rule, which reinforces somehow the idea that in these existing type systems, you're very much syntactically matching the type against the term to establish typability. Okay, fine. This is a very technical property in some sense. Why does this matter? Well, we can make two observations now. The first observation is by synthesizing the G prime from G as part of the premise, but not the conclusion. The syntax of G itself, or the structure of G internally, it doesn't matter at all. We care only about the transitions of G, and whether or not this is a global type or a configuration of a Petri net, we really don't care, right? And then the follow-up observation is that, yeah, if we don't care about the internals of G, then we can basically just treat it as an opaque state of a label transition system. And once we made that observation, we sort of thought, okay, that's kind of nice. Can we formulate the whole meta theory in terms of arbitrary label transition systems? So, arbitrary label transition systems, well, the arbitrariness, that turns out to be a bit difficult because we need to know at least some things about the transition structure. And so we defined a number of, let's say, sanity conditions that each such an LTS should satisfy, which we call together well-behavedness. Now, I don't want to go into the details of what those conditions exactly are, but the things that you can think of is, for instance, we need some kind of confluence, we need some kind of determinism, we need them to be finite, those kind of things. Okay, fine. But you can define this, well-behavedness. And then the main theorem is that we have progress and preservation for states of well-behaved label transition systems. So at this point, we no longer care about where G exactly comes from or what it is. It can be just a state in a transition system. This is the general case. And then for the special case, we separately prove that if such a G happens to be a global type, then the transition system that you can generate for G using the existing operational semantics in the session types literature, those LTSs are well behaved. So this progress and preservation result, it does carry over from the general case to the special case. And that's essentially it. This is again the slide with the contributions. I won't go through them in detail again. There's some future work I can mention, but I think I ran out of time, so let me not do that. Thank you for your attention.
Thank you very much. I think we have time for a question, but if the next speaker could start setting up, that'd be great.
Can you formulate progress and preservation as a simulation property?
I think yes. I think yes. We haven't tried it, but it is very close to a kind of simulation, yes.
Okay, so our next speaker is Johan Rosen, who'll speak about bounded sort polymorphism. Thank you very much.
Okay, thank you. So, yes, today I'm going to speak about bounding sort polymorphism so that we can actually use it in real life, right? And so, yeah, but before that, I'm going to open a small parenthesis about, we are all computer scientists here, and we know that some of us can be very opinionated, like Stephanie said in her talk an hour ago. Like, some people will defend type conversion with their body, and others will swear by untyped conversion, right? And, well, even if we are mostly a very opinionated community, we more or less agree on one point, that code duplication is harmful, right? Or, it's been put much more elegantly than I can say in this book named Principle of Programming Languages. which reminds me of something, but I can't quite put the finger on, right? Or also said very concisely by Dijkstra, saying 2 or more, use a 4. Very nice, right? And so this is, I mean, programming languages have been evolving to avoid this kind of duplication. I mean, even imperative languages have something like higher order functions or even polymorphism, right? But at some point in the evolution, there was a divergent path where multi-sorted type theories arrived, and there, duplication was somehow, well, okay, I don't know why, right? So first, yes, what do I mean about multi-sorted type series? So usually, we have typical Martin-Löf dependent type system with dependent functions and a hierarchy of universes of types, right? And we can even add inductive and records, their elimination rules, introduction rules, projections, and so on. But in multi-sorted type series, instead of having this whole type hierarchy, what we have is universe hierarchies, where they are parameterized by a sort S, which is in some kind of set G of ground sorts. So this set of ground sorts, we say that what we want to have is a distinguished sort type for which, well, we can type other universes with at the next universe level. We also have predicative sorts and impredicative sorts. By impredicative, I mean that the universe, we only care about the universe level of the codomain when doing dependent function. So, yeah, this is actually a model that quite naturally models current proof assistants. Like, for instance, we have Agda that has 2 predicative hierarchies of set and prop, Lin that has 1 predicative hierarchy type and 1 impredicative hierarchy prop, and ROG that has also some same stuff as Lin but with edge prop. So this is nice. We have multiple hierarchies to mean multiple things, like for instance, with types or sets, well, we have computational contents, we put Booleans in it, integers, natural numbers, and so on, and we also put, well, types, right? And in prop or S-prop, we can have proofs sometimes irrelevant. So this means that basically we can't just pass from one hierarchy to another. We have to have some kind of restrictions because, for instance, we don't want to produce computational content from maybe irrelevant proofs. So here, what we say is that, okay, we cannot say, yes, well, what I just said, right? But in practice, what this means is that this kind of stuff leads to duplication. So why is it the case? Well, I mean, it's because, for instance, if you want to write a sum type, you can say, I want everything to be computational, right? And so you write it like this. But yeah, maybe you want to write a logical disjunction, and in this case, you want everything to be propositional, and you write it like that. Or, well, you could do a mix of both, saying, okay, I want my sum type to be computational, but I don't care about the values it has, and you say, oh, I have some stuff that is propositional and some stuff that is computational. And so this is actually examples that we can find in ROC standard library for more than 20 years, right? Okay, and so last year at POPL', there was this magnificent paper saying, okay, we can avoid duplicating such inductives. So how do we do that? Well, instead of having sorts, static sorts, we can quantify prenexly over sorts and say, for instance, we have A that is in the sort SL, B in the sort SR, and the target sort is S. And so using this, so this basically makes all the previous combinations of all the different sorts. And yes, so here maybe the annotations are a bit scary, right? But okay, so on the right, we have universe levels that I won't use anymore in this talk because it's totally orthogonal to what I'm going to be talking about. And what we are going to focus on is sort level polymorphism that is on the left of the brackets here, okay? And so all of this is universe polymorphism, but yeah, we are only focused on sort polymorphism here. But the problem is that even with this, we can't avoid duplication. This is not enough. And why is this the case? Well, for instance, we can have an even more scary term for the eliminator of this generic sum type. Here, we have U that is a sum type in the sort S, and we want to create a content in the sort S prime. Okay, so we quantify over all of these sorts, and we write this term. But if this was accepted, we could instantiate, for instance, S with prop and S prime with type. And if we did that, then we can now create computational content from proofs. So the very stuff that we forbid at the beginning because it would make everything consistent, right? And yeah, I mean, we could also say S is instantiated by S prop, and we have an even simpler proof of fault. So what this means that now we have to declare all the valid eliminators by hand, which is as bad as it was before. Like, yeah, we have hidden some of the stuff, but it comes right back at us, right? And so there is also another problem of pre-next sort polymorphism as it was presented last year, is that in the system that's sort poly, I refer to it like that now, there is no principal sort assignment for a very simple term that is a mapping between two lists. Because here, so in ROC, we have that the lists, we have that type, we can create everything from types. So here, if list A lives in type, then you can create a list of B. But maybe list A lives in the same sort as list of B, and so it can also create a list of B. And so there is no instance that supersedes the other, and so yeah, this is, there is no most generic sort assignment for this term, right? And so what we did is to introduce bounds in this sort polymorphism system to allow writing the most generic terms, so basically to have terms with the principal sort assignment, and to infer these terms so that we don't have to put all these scary annotations of the previous terms. So we show that it has relative consistency with respect to the sort poly system, and actually it has the same logical power. So yeah, in this talk I'm going to focus on explaining a bit about the relative consistency because yes, it shows some hidden properties of the system. Okay. And so what we propose to bound sort polymorphism is to add elimination constraints between sorts. So here, when we want to define the most generic eliminator for the sum type, well, we say, okay, we want S to eliminate into S prime. So here we call that S is a sort of the sum of the term of the sum type that we want to eliminate, and S prime is a sort of the type we want to create. And so if we say, okay, we can now create elements from the sort S prime from elements of the sort S. And so this term is type checking. So yeah, I mean, elimination constraints between sorts is something that is also pretty natural in current proof assistance. I mean, for instance, in ROC, there was this table of elimination between sorts. And yeah, I mean, this is a natural extension of the theory And we can see that in Agda, well, we have these elimination constraints like set eliminates to set, set eliminates to prop, prop eliminates to prop, and we can do more or less the same stuff for lean and rock. Yes. Okay, but so this is very natural, but actually it induces some strange stuff. So for instance, if we have sort S, such that S prop, so which is proof irrelevant in rock, so that S prop eliminates into S, we can prove that S has propositional proof irrelevance. But better, we can actually show that it has definitional proof irrelevance. So how do we do that? So assuming that we have a type in the sort S and X and Y, two terms of type A, well, we want to show that X is Y. But actually, we can define a function that takes Booleans in S prop and returns values of type A. And we say, okay, if the Boolean in input is true, then we return X. If it's false, we return Y. And what we actually have to prove now is that f of true is equal to f of false, because f of true is X, f of false is Y. But here, because S prop is proof irrelevant, it means that true is actually definitionally equal to false. And so we can just say but it's reflexive, right? So here, X is definitionally equal to Y, which means that when we have such elimination constraints, for the type checking to be correct, we have to inherit all the conversion rules of the sort that is above. Okay. And so this is kind of the hard part of the consistency theorem. So here, we assume that the system of sort poly is consistent, and then we show that there is no closed term of type bottom in a consistent sort. So maybe this sounds like a tautology, but yeah, actually, it's not really a tautology. And also, yes, there is in this statement, there is no notion of the ground sorts G when we say, actually, we work in a system with abstracted ground sorts. So this hides some things. So yeah, why is this not a tautology? It's because actually what we say is not, we say that S is a consistent sort when S eliminates to a ground sort that is assumed consistent, like S prop or type in rock, not when there is no proof of false in it. And yeah, so we will see that this theorem holds if we have some conditions, of course, on the set of ground sorts. So let's talk about these conditions. So what we want to do is that if we have a closed term T of type bottom in the sort S, we want to instantiate away the sort variables so that we get a term without elimination constraints and a term in sort poly that is, well, of type false. So the question is, but how can we do that? Well, the first answer is to say, maybe we can have some kind of initial sort that I name data, which eliminates into every ground sort. And with this, we say, okay, we instantiate every S using data. So this approach doesn't work because, well, of the conversion rule inheritance that we saw just before. What if at some point we have to instantiate a sort at data, and well, actually in the typing rule, it used the conversion rules of S prop. I mean, it's not possible anymore. So seeing this, we can say, okay, maybe what we have to do is to instantiate every sort using the ground sort that's directly above it in the elimination hierarchy. So, I mean, yes, this kind of works, but actually not alone. We need conditions on the set of ground sorts. So first, this sort that's directly above S may not always exist. Like in this case, well, we have a sort S prime, such that S prop eliminates into S prime and G eliminates into S prime. Morally, well, here G is some kind of ground sort, and yes, you can have any conversion rules you want on this ground sort. And maybe, well, the conversion rules of G and S prop are not compatible. And so, yeah, we cannot instantiate S prime to S prop, nor can we instantiate it to G. The second case is that, yes, maybe we have a sort S prime that eliminates prop, and we have two other sorts, type and G, that also eliminate prop. So what should we instantiate S prime with? I mean, type or G, both, I don't know. So in the first case, what we do is that we require S prime, or I mean every sort variable in the elimination graph, to be dominated in the graph theoretic sense, which basically means that there can only be one thing directly above. So yeah, if we remove the elimination from S prop to S prime, then S prime is dominated by G, or if we remove the elimination constraint from G to S prime, then S prime is dominated by S prop, and if we add a constraint from prop to S prime, then, well, S prime is still dominated by S prop. And on the other side, well, what we can do is actually have this initial sort that was proposed to say, okay, we have data that eliminates into everything, and then maybe, and then here we can say S prime can just be instantiated by data. So let's come back to this theorem. Now, how do we instantiate the sort variables? So first, we have to ensure the existence of the ground sorts that directly above every sort. And so, yes, and we also need to take care of strays and so have this initial sort data. So in this case, well, what we can do is simply instantiate every sort variable by taking the dominant ground sort, so the sort that's directly above every sort variable, and use the initial sort if there are no such dominants. And I mean, this doesn't actually conclude the proof, but there are some gory details that I'll spare you. And so what we actually did was that we made that a reality in the ROC proof assistant. And so, yes, actually, there is way more than what I told in this talk, but the main point is that if you want to follow the integration of elimination constraints and actually be able to use sort polymorphism, you can follow the RFC. And I mean, some of the stuff has already been integrated for ROC 9.2. So we have a small manual prohibition of S prop eliminates to S that we cannot do at the moment because, well, conversion issues. And yes, we also have elaboration to get the principles of assignment and to avoid all of these annotations. That's a current PR. So there is some downside is that we have a bit of regression, even in the monomorphic case of performances, because instead of checking eliminability through a static table, we do it through a graph. So yeah, we lose some time with this, and we have some bigger structures during the elaboration and all of this stuff. And so to conclude, what we have done is to extend the type system of sort poly so that we have relative consistency with the system, actually the same logical power. We have also principal sort assignments and an elaboration procedure that yields this principal sort. And what we want to do in the future work is to adapt the tactics and libraries to use this system of bounded sort polymorphism. and to explore a bit more of the meta theory, for instance, with co-eliminability and conversion, and also probably add support in other proof assistance. Thank you.
Thank you very much. Do we have any questions?
So you said that you need a domination constraint to manage to prove the theorem.
Yes.
But is it the case that if you don't have the domination constraint, then the theorem is false?
In general, yes, I think so. Yes, I don't have an example right now, but I think I do.
In your presentation, you said you need the initial sort data to make it a unique like predecessor. So is this data compatible with existing code bases? So if you infer the data as an assignment, should you reject it, or should you because you don't really have something data sort, right?
Sorry, can you repeat, please?
So you say you need to add an extra data sort to make it work. So if like your infer assignment with a data sort, so how it corresponds to like current raw code bases, because you don't really have this data sort in any existing code. So like if you infer this, should it be rejected or?
Yes.
Oh. So it's like an arrow sort in some sense.
Yes.
Like, okay, thank you.
Okay, I think there are no more questions, in which case we'll thank the speaker. Thank you very much.